beyond our sky, beyond the stars we see, lies a deeper mystery. Older than light, more profound than thought. Here, the universe holds its ultimate secret, a place where time itself had no meaning and silence was absolute. Imagine a state so empty, so devoid of everything, it swallows even existence. How did the universe begin from absolute nothingness? Our current understanding of reality tells us that something can't just be created from nothing, out of thin air. So how did the universe start? Before we begin this exploration, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating journey to the beginning of the universe. The concept of nothing seems simple at first glance. We might picture an empty box, a room with no furniture, or the vast, dark expanse of space between stars. In common language, nothing implies an absence, a void where something should or could be. However, in a scientific context, especially when discussing the origin of the universe, the meaning of nothingness becomes far more complex and profound. It challenges our everyday intuition and forces us to consider the very fabric of reality. Scientifically, nothing is not merely an empty container. It can imply the absence of the container itself, the absence of space, time, matter, energy, and even the fundamental laws that govern their existence. The vacuum of space, for instance, is often considered empty, yet it is anything but truly nothing. Even in the deepest reaches of interstellar space, far from any star or galaxy, there are still faint traces of hydrogen atoms, cosmic background radiation from the Big Bang, and gravitational fields. Furthermore, according to the principles of quantum mechanics, a truly empty vacuum cannot exist. This is due to the Heisenberg uncertainty principle, a core idea in quantum physics, which states that one cannot simultaneously know with perfect accuracy certain pairs of properties of a particle, such as its exact position and momentum. Applied to energy and time, this principle suggests that energy cannot be zero for an extended period in a given volume of space. This leads to the phenomenon of virtual particles. Virtual particles are pairs of particles and antiparticles that spontaneously pop into existence from seemingly nothing in the vacuum, exist for an incredibly brief moment, and then annihilate each other, returning their energy to the vacuum. These fleeting appearances and disappearances are not mere theoretical curiosities, their effects are measurable. One of the most famous pieces of evidence for the quantum nature of the vacuum is the Casimir effect, first predicted in 1948 by the Dutch physicist Hendrik Casimir. The Casimir effect demonstrates that two uncharged, perfectly parallel conducting plates placed very close together in a vacuum will experience a small but measurable attractive force. This force arises because the plates restrict the types of virtual particles that can appear in the tiny gap between them, compared to the space outside. The resulting imbalance in quantum fluctuations creates a net pressure pushing the plates together. This means that even the vacuum of space, which appears empty to our senses, is a bustling arena of temporary particle creation and annihilation, possessing what is known as zero-point energy. Therefore, the vacuum of space, full of virtual particles and zero-point energy, is very far from absolute nothingness. It is a dynamic and energetic background. When cosmologists speak of the universe beginning from nothing, they're usually referring to a state prior to the existence of space and time as we understand them. This is a level of nothingness that goes beyond even the quantum vacuum within our existing universe. Our universe is fundamentally defined by its space-time fabric, the four dimensions that dictate where and when events occur. If there was truly nothing before the Big Bang, it would imply the absence of this very fabric. There would be no where for anything to exist, and no when for any event to take place. This concept is extremely difficult to grasp because our minds are wired to think within the confines of space and time. We instinctively imagine before the Big Bang as some empty space waiting for something to happen. But if time itself began with the Big Bang, then the concept of before loses its usual meaning. It's not a matter of an empty stage, it's the absence of the stage itself. The idea that space and time themselves emerge from a state where they did not exist is a central tenet in many cosmological theories. One perspective suggests that the universe did not expand into pre-existing space, but rather that space itself was created and expanded. In this view, the nothing from which the universe emerged was a state utterly devoid of spatial dimensions, temporal progression, and even the fundamental physical laws that govern our current reality. It would be a state of utter non-existence for everything we consider real. However, some scientific discussions also consider different shades of nothing. For instance, a pure mathematical nothing would be the empty set containing no elements. But physics deals with physical reality. The question then becomes, can physical reality arise from such an absolute mathematical void? Or does there need to be some underlying potential, some fundamental principle, even if it's not physical in our current sense? The concept of a true nothing would imply that even the laws of physics, like gravity or electromagnetism, did not exist. If there were no laws, how could anything spontaneously come into being, following rules that were not yet established? Some modern theories propose that what we perceive as nothing might actually be a more fundamental, unified field or a higher dimensional reality from which our universe, with its specific laws and dimensions, somehow crystallized or bubbled off. In such scenarios, the universe didn't come from absolute non-existence, but rather from a different, perhaps more complex or abstract form of existence that we're only beginning to conceptualize. These ideas suggest that the nothing from which the universe emerged was not an absolute void, but rather a different state of reality, a pre-geometric or pre-physical state where the conditions for our universe were latent. The challenge of defining nothing in the context of cosmic origins is one of the deepest problems in science and philosophy. It forces physicists to confront the very boundaries of their theories and the limits of human understanding. The fact that the quantum vacuum is not truly empty, but rather a teeming sea of virtual particles, provides a potential mechanism for something to arise from almost nothing. If the universe began from a quantum fluctuation in a pre-existing field or quantum foam, then it didn't strictly arise from absolute nothingness, but from a quantum state that is vastly different from our current universe. This distinction is crucial. If the universe started from a true absolute nothing, where not even quantum fields existed, then the question of why anything at all becomes even more profound and difficult for science to answer using current frameworks. The concept of nothing has fascinated and puzzled thinkers across various cultures and throughout human history. From ancient philosophers contemplating existence to modern scientists probing the origins of the universe, the idea of absence, void, or non-being has taken on many forms. Understanding these different conceptualizations is key to appreciating the scientific journey toward explaining how our universe could have begun from what appears to be nothing. In ancient Greece, philosophers grappled with the idea of nothingness. Parmenides, a pre-Socratic philosopher, famously argued that true nothingness could not exist. For him, what is, and what is not. To speak of nothing was to speak of what does not exist, which was illogical and impossible. He believed that change and motion were illusions because they implied that something could come from nothing or go into nothing. In contrast, the atomists, like Leucippus and Democritus, proposed that the world was made of indivisible particles called atoms, moving through an empty void. For them, this void was a necessary space for atoms to move, representing a physical form of nothingness, albeit one that existed within something else, namely space itself. Aristotle later largely rejected the concept of a vacuum, arguing that nature abhors a vacuum, and that any apparent void would immediately be filled. His views held sway for many centuries. In Eastern philosophies, particularly in some schools of Buddhism, the concept of emptiness, sunyata, is central, but it is not a nihilistic nothing. Instead, it often refers to the absence of inherent existence or self-nature in phenomena. It's a profound understanding that things are interdependent and impermanent, not a literal void, but a state of dynamic potentiality and interconnectedness. This emptiness is full of possibility, not absolute non-being. During the Middle Ages, the Christian concept of creation ex nihilo, meaning from nothing, became dominant. This theological idea posited that God created the universe not by shaping existing matter, but by bringing it into being from a state of absolute non-existence. This was a radical departure from many ancient creation myths that involved shaping existing primordial matter or divine beings. This theological concept of nothing was a true, absolute void, a state of non-being before divine creation. The scientific revolution brought new ways of thinking about space and absence. Isaac Newton, in the 17th century, conceived of space as an absolute empty container, distinct from the matter within it. For Newton, this absolute space was a vast, unchanging void, the arena in which physical events unfolded. This aligns somewhat with the atomist view of a physical void through which objects move. However, even Newton's absolute space, while empty of matter, was still a something, a pre-existing backdrop for the universe. The 18th and 19th centuries saw the development of field theories, particularly in the electromagnetism. Scientists began to realize that even in seemingly empty space, there were electric and magnetic fields. This challenged the idea of space as a mere void, suggesting it had its own properties and dynamics. Michael Faraday's work on fields and James Clerk Maxwell's unification of electricity and magnetism showed that empty space could transmit energy and forces, implying it was not truly nothing at all. The early 20th century, particularly with Albert Einstein's theories of relativity, revolutionized the understanding of space and time. Einstein showed that space and time are not separate, static entities, but are interwoven into a dynamic fabric called space-time. This fabric can be warped by matter and energy, giving rise to gravity. In this view, empty space-time is still a physical entity, capable of bending and influencing matter. It is a fundamental component of the universe, certainly not nothing. However, it was quantum mechanics, developed in the early 20th century, that truly transformed the scientific understanding of the vacuum. As discussed in the previous section, quantum field theory posits that even the deepest vacuum is not empty. Instead, it is a bustling sea of quantum fields, constantly fluctuating. Particles are seen as excitations of these fields. The vacuum state is the lowest energy state of these fields, but even this lower state is not zero energy. This zero-point energy and the continuous appearance and disappearance of virtual particles mean that quantum nothingness is far from inert. The observable effects of these fluctuations, such as the Casimir effect, provide strong evidence for this dynamic quantum vacuum. This quantum understanding of nothing has profound implications for cosmology. If the vacuum is inherently unstable and capable of generating particles and energy, it provides a scientific framework for how the universe might have originated without necessarily invoking an absolute pre-existing void. Some theories suggest that our universe could have arisen from a quantum fluctuation in a larger pre-existing quantum vacuum or multiverse, essentially a bubble expanding out of a quantum foam. In this view, the universe did not come from true nothing, but from a different, more fundamental something that underlies all possible universes. The journey of the idea of nothing in science, therefore, moves from a simple philosophical absence to a physical void, like Newton's absolute space, to a dynamic, fluctuating quantum vacuum. The scientific nothing is rarely a true absolute void. Instead, it has become an increasingly complex and active entity, capable of generating particles, energy, and potentially even entire universes. The most challenging aspect of nothing for science remains the concept of a state where not only matter and energy, but also space, time, and physical laws themselves did not exist. Whether such an absolute non-existence is a meaningful concept, or whether there must always be some underlying substrate or potential, remains a frontier of scientific and philosophical inquiry. The modern scientific understanding leans towards a nothing that is always something, in a profound and unexpected way, filled with latent possibilities. Our human senses are remarkable tools that allow us to interact with and understand the world around us. We see light within a narrow spectrum, hear sounds within specific frequencies, feel touch, taste flavors, and smell odors. These senses evolved to help us survive and thrive in our particular environment, but they provide only a tiny glimpse into the vast and often counterintuitive nature of the universe. These senses evolved to help us survive and thrive in our particular environment, but they provide only a tiny glimpse into the vast and often counterintuitive nature of the universe. To truly comprehend the universe's beginning and its fundamental workings, we must venture far beyond what our senses can perceive, relying instead on sophisticated instruments, complex mathematics, and abstract reasoning. Consider the scales of the universe. Our everyday experience ranges from the size of a grain of sand to the distance we can walk in a day. However, the universe operates on scales that defy direct human experience. At one end, we have the incredibly small, the realm of subatomic particles. An electron, for instance, is so tiny that it has no measurable size. It behaves more like a point. Protons and neutrons, which make up the nucleus of an atom, are themselves composed of even smaller particles called quarks, which are bound together by the strong nuclear force. The distances involved here are measured in picometers, 1/1,000,000th of a meter, or even femtometers, 1/1,000,000th of a meter. Our eyes cannot see these particles, and our hands cannot feel them. Our intuition, based on interacting with everyday objects, completely breaks down when trying to imagine how these particles behave, how they can exist as both particles and waves, or how they can seemingly tunnel through barriers. At the other end of the spectrum is the incredibly large, the cosmic scale. Our planet Earth is just one of 8 planets orbiting our Sun. Our Sun is one of hundreds of billions of stars in our Milky Way galaxy, and our galaxy is just one of hundreds of billions of galaxies in the observable universe. The distances are staggering. Measured in light years, the distance light travels in 1 year, approximately 9 quadrillion kilometers. The nearest star to our Sun, Proxima Centauri, is over 4 light years away. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light years away. The very edge of the observable universe is estimated to be about 46 billion light years distant. Our brains, accustomed to distances we can walk or drive, struggle to truly grasp these immense scales. We cannot visually perceive the curvature of space-time, nor can we directly witness the expansion of the universe on such vast cosmic scales. Beyond size, our senses are also limited by extreme conditions. The universe at its birth was a place of unimaginable extremes, utterly alien to anything we experience. The temperatures in the earliest moments of the Big Bang were so high that all matter as we know it would have instantly vaporized. We are talking about temperatures of trillions, quadrillions, even quintillions of degrees Celsius, far hotter than the core of any star. At such temperatures, particles move at nearly the speed of light, and the fundamental forces of nature that are distinct today, like electromagnetism and the strong and weak nuclear forces, are thought to have been unified into a single combined force. Our senses cannot register such heat. Any interaction would be instantaneously destructive. To study these conditions, physicists rely on particle accelerators, like the Large Hadron Collider, which can recreate fleeting glimpses of these extreme energies, but even these machines only scratch the surface of the universe's initial state. Similarly, the densities were beyond comprehension. All the matter and energy of the observable universe were packed into an infinitesimally small volume, smaller than an atom. The concept of something so dense that even light cannot escape, like inside a black hole, is already difficult to visualize. The early universe was far denser. Under such extreme density, the very laws of physics as we understand them, including those of general relativity, break down, pointing to the need for a more fundamental theory, like quantum gravity, which is still under development. Time itself behaved differently. Our senses perceive time as a linear progression: past, present, future. But in the first moments of the universe, events unfolded in fractions of a second so small they are almost meaningless to us. The Planck time, the smallest meaningful unit of time in physics, is 10 to the negative 43 seconds, 0.00, with 42 zeros after the decimal point, followed by a 1. Events crucial to the universe's fundamental properties, like cosmic inflation, are believed to have occurred within these incredibly tiny time intervals. Our human perception of a second is already fast, let alone events occurring in less than a trillionth of a trillionth of a trillionth of a second. Furthermore, much of the universe is composed of things entirely invisible and undetectable by our direct senses. Dark matter, for example, makes up about 27% of the universe's mass. We cannot see it, touch it, or smell it. It does not interact with light or other electromagnetic forces, hence dark. We only know it exists because of its gravitational effects on visible matter, such as how galaxies rotate faster than they should if they only contain the stars we see. Similarly, dark energy, an even more mysterious component, makes up about 68% of the universe's total energy content. It is believed to be responsible for the accelerating expansion of the universe. Again, we cannot sense it directly. Its presence is inferred from its effects on the large-scale structure and expansion rate of the cosmos. To explore these unseen realms, scientists have developed powerful tools that extend our senses by many orders of magnitude. Radio telescopes detect electromagnetic waves far longer than visible light, revealing distant galaxies and the faint glow of the cosmic microwave background. X-ray and gamma-ray telescopes observe the most energetic phenomena, like black holes and supernova explosions. Particle detectors sense subatomic particles that pass through us constantly. Gravitational wave observatories detect ripples in spacetime itself, caused by cataclysmic cosmic events. These instruments translate the imperceptible into data that scientists can analyze and interpret using the language of mathematics. Mathematics is the indispensable language for going beyond our senses. Concepts like four-dimensional spacetime, quantum fields, and the probabilistic nature of subatomic particles cannot be fully grasped through mere imagination or sensory analogy. They require abstract mathematical frameworks that describe their behavior and interactions. While analogies can help bridge the gap between abstract concepts and our familiar world, like thinking of spacetime as a stretched rubber sheet, they are ultimately limited and can be misleading if taken too literally. The common understanding of empty space usually brings to mind a vast, silent void, perhaps the vacuum of outer space where astronauts float freely. We might picture a room cleared of all furniture, leaving behind nothing but air and walls. Yet, in scientific terms, especially when considering the origin of the universe, the concept of empty space is far more complex and elusive than this simple image suggests. For cosmologists, the question is not merely about an empty region within our universe, but about whether space itself existed before the universe came into being, and how it might have originated. Historically, the idea of space evolved considerably. In ancient philosophy, thinkers like Aristotle believed that a true vacuum or empty space could not exist. He argued that nature abhors a vacuum, and any void would immediately be filled. His views influenced thought for centuries. Later, in the 17th century, Isaac Newton introduced the concept of absolute space in his laws of motion and universal gravitation. For Newton, space was like an invisible, infinite, and unchanging container that existed independently of anything within it. It was a fixed, immovable backdrop against which all events unfolded. This absolute space was considered empty in the sense that it contained no matter, but it was still a pre-existing something, a fundamental arena for the universe. Even then, critics like Gottfried Leibniz argued against absolute space, proposing instead a relational view where space was merely the collection of relationships between objects, rather than an independent entity. The 20th century brought a profound revolution in our understanding of space, largely thanks to Albert Einstein's theories of relativity. Einstein demonstrated that space is not a passive, unchanging container, but is intimately intertwined with time, forming a dynamic four-dimensional fabric called space-time. This space-time fabric is not empty or rigid. It can be warped and curved by the presence of mass and energy, and this curvature is what we perceive as gravity. So, even seemingly empty regions of space are actually active participants in the universe's dynamics, constantly being shaped by the matter and energy within them. This means that space, even without matter, is a physical entity with properties, quite unlike a simple void. Furthermore, quantum mechanics, developed in the early 20th century, introduced another layer of complexity to the idea of empty space. According to quantum field theory, what we perceive as a vacuum is not truly empty. Instead, it is teeming with activity at the subatomic level. This quantum vacuum is filled with fluctuating energy fields from which virtual particles spontaneously pop into existence for incredibly brief moments, only to vanish again, returning their energy to the vacuum. These fleeting particle-antiparticle pairs are not just theoretical constructs. Their effects are measurable, for example, in the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force due to the imbalance of these virtual particles. This means that even in the most empty regions of our current universe, space possesses zero-point energy and is a vibrant dynamic quantum foam far from absolute nothingness. When cosmologists discuss the origin of the universe from nothing, they are typically referring to a state that existed before space itself came into being. This is a crucial distinction. It is not about an empty region within space, but about the theoretical absence of space altogether. The prevailing scientific model for the universe's origin, the Big Bang theory, suggests that space, time, matter, and energy all originated simultaneously from an incredibly hot and dense state. In this view, space did not pre-exist as a stage for the Big Bang. Rather, space itself was created with the Big Bang and has been expanding ever since. To illustrate this, consider the common analogy of an expanding balloon. Imagine dots drawn on the surface of a deflating balloon. As the balloon is inflated, the dots move farther apart. The surface of the balloon represents space. The key point is that the dots, galaxies, do not expand into some larger pre-existing space outside the balloon's surface. Instead, the surface itself is expanding. If you were an ant living on the surface of the balloon, your entire universe would be that two-dimensional surface. You would have no concept of outside the surface. Similarly, in our three-dimensional universe, as space expands, it is not expanding into anything beyond itself. Space is the expansion. If we reverse this expansion, we arrive at a point where space would have been infinitesimally small, or perhaps, in some theoretical models, non-existent. The idea that space itself originated from a state where it did not exist is deeply challenging to our human intuition, which is inherently spatial. We tend to visualize before the Big Bang as some empty void where nothing existed, but this still implies a spatial container. If space itself did not exist, there was no where for anything to be. This means the universe did not begin in space, but rather that space began with the universe. It is an emergent property, something that arose from more fundamental pre-spatial conditions. Theoretical frameworks, such as some approaches to quantum gravity like loop quantum gravity, explore the possibility that space itself is not continuous, but is made up of discrete tiny units, like individual atoms of space. If this were true, then before space existed could mean before these fundamental units coalesced or became organized in a way that gives rise to what we perceive as continuous space. In such models, space is not a void, but a fabric woven from fundamental quantum components. When these components were not organized or did not exist, neither did space. The smallest possible unit of space is theorized to be related to the Planck length, an incredibly tiny distance, about 100 quintillion trillionths of a meter, below which the concept of smooth space breaks down and quantum effects dominate. Therefore, the scientific understanding of empty space ranges from a dynamic quantum vacuum filled with virtual particles within our universe to the profound idea that space itself was not a pre-existing emptiness, but an emergent property that came into being with the universe's origin. The question of how space emerged from a truly non-spatial state remains one of the deepest mysteries at the forefront of modern cosmology, pushing the boundaries of what we can conceptualize about the ultimate beginning. The concept of time seems inherently straightforward in our daily lives. We experience it as a linear progression. Moments flow from the past through the present and into the future. We measure it with clocks, and we organize our lives around its relentless march. However, when cosmologists discuss the origin of the universe, they often speak of a moment before time began, a phrase that challenges our everyday understanding and requires a complete re-evaluation of what time truly is. This is not simply about a period when nothing happened, it is about a state where the very concept of when, or duration, had no meaning. For centuries, time was largely conceived as an absolute and universal entity. Isaac Newton, in the 17th century, described absolute, true and mathematical time as flowing uniformly and independently of anything external. For Newton, time was a universal clock, ticking away identically for everyone and everything, everywhere in the cosmos. It was an unchangeable backdrop against which all physical events unfolded. This view provided a solid foundation for classical physics and aligned well with human intuition. However, Albert Einstein's theories of special and general relativity, developed in the early 20th century, shattered this classical notion of absolute time. Einstein showed that time is not separate from space, but is interwoven with it into a four-dimensional fabric called space-time. Crucially, Einstein demonstrated that time is relative. Its passage can vary depending on an observer's motion or the strength of gravitational fields. For example, clocks tick slower in stronger gravitational fields, or when moving at very high speeds relative to an observer. This phenomenon, known as time dilation, means there is no single, universal clock. Time is not an independent entity, but is inextricably linked to the physical processes and gravitational conditions of the universe. This relativistic understanding of time has profound implications for the universe's origin. The Big Bang theory, the leading cosmological model, posits that the universe began from an extremely hot and dense state, approximately 13.8 billion years ago. In this model, space, time, matter and energy all came into existence simultaneously at that moment. This means that, before the Big Bang is not a temporal period. If time itself originated with the Big Bang, then the word before loses its conventional meaning. It's not that there was an empty stretch of time waiting for the universe to appear. Rather, the very dimension of time did not exist in the same way it does now. To grasp this, consider an analogy often used in cosmology: the Earth's surface. If you ask, what is north of the North Pole? The question has no meaningful answer within the context of the Earth's surface. The concept of north originates at the North Pole and moves away from it. Similarly, if time began at the Big Bang, asking what happened before, it is like asking what is north of the North Pole of time. The concept of before simply does not apply. Time, as we understand it, is a dimension of the universe, and if the universe began, then so did that dimension. Cosmological time, the time we use to describe the age and evolution of the universe, begins at the Big Bang. This progression is closely tied to the universe's expansion and cooling, and importantly to the concept of entropy. The second law of thermodynamics states that entropy, or disorder, always increases in a closed system. The universe began in a state of extremely low entropy, a highly ordered, compressed state, and has been increasing in disorder ever since. This irreversible increase in entropy provides a cosmic arrow of time, dictating the direction in which time flows. If the universe started from a low entropy state, and if time is fundamentally linked to the increase of entropy, then the beginning of the universe is also the beginning of this thermodynamic arrow of time. Some theoretical approaches to quantum gravity, which attempt to unify general relativity with quantum mechanics, suggest even more radical possibilities for time's nature at the universe's very beginning. For instance, Stephen Hawking's no-boundary proposal suggests that at the very earliest moments time might have behaved like another dimension of space, rather than a distinct temporal dimension. In this scenario, there would be no sharp boundary or beginning point for time in the traditional sense, just as the surface of the Earth has no edge. This would eliminate the problem of what caused time to start, as it would not have had a distinct starting point but would smoothly transition from a timeless space-like state. Other quantum gravity theories, such as loop quantum gravity, propose that time, like space, might not be continuous, but composed of discrete fundamental chunks, or events. In such models, time would be an emergent phenomenon, arising from the interactions of more fundamental quantum constituents, rather than an underlying continuously flowing river. If time is emergent, then before time began could refer to a state where these fundamental interactions had not yet given rise to what we perceive as temporal progression. Furthermore, some cosmological models, such as cyclical or bouncing universe theories, propose that our universe is not the first but one in an infinite series of universes, each emerging from the collapse of a previous one. In such scenarios, time might not have a singular beginning or end, but would be perpetual, passing through cycles of expansion and contraction. However, even in these models, the current cycle of the universe would have a specific beginning point for its current expansion, which is the Big Bang for our current cosmic epoch. The philosophical challenge of conceiving a state before time began is immense because our consciousness, memory, and experience are fundamentally temporal. We understand existence through change and sequence. To imagine a state without change, without sequence, without when, stretches the limits of human thought. Yet modern cosmology forces us to grapple with this very idea that time is not an external container that always existed, but an intrinsic dimension that emerged with the universe itself. Understanding before time began is therefore not about a journey backward to an earlier point on a timeline, but rather about comprehending the origin of the timeline itself. The term cosmic egg, or primeval atom, refers to a theoretical concept describing the incredibly dense and hot state from which our universe is believed to have expanded. This idea was first proposed in 1927 by Georges Lemaitre, a Belgian priest and physicist, who developed what we now call the Big Bang theory. Before Lemaitre, many scientists, including Albert Einstein, favoured a static, unchanging universe. Lemaitre's cosmic egg provided a revolutionary alternative, suggesting a dynamic, evolving cosmos with a definite beginning. Imagine all the matter and energy that currently exists in our vast observable universe. Every star, every galaxy, every particle, and every form of radiation. Now picture all of that immense content compressed into an unimaginably tiny volume, smaller than a single atom, perhaps even as small as the fundamental Planck length, 100 quintillion trillionths of a meter. This is the essence of the cosmic egg. It was not an object in space, but rather a state where space itself, along with time, began to exist and expand from this ultra-compressed point. The properties of this cosmic egg would have been truly extreme, far beyond anything we can experience or even easily imagine in our current universe. Firstly, it would have been incredibly hot. The temperature of the cosmic egg would have been almost infinite, reaching quadrillions, or even quintillions, of degrees Celsius. At such extreme temperatures, matter as we know it could not exist. Atoms, which are made of nuclei and electrons, would have been impossible to form. Even the nuclei of atoms composed of protons and neutrons would have been unstable. Instead, the universe would have been a superhot plasma of fundamental particles, such as quarks and leptons, like electrons and neutrinos, and their antimatter counterparts, along with an intense bath of radiation. All particles would have been moving at nearly the speed of a light, constantly colliding and interconverting from energy to matter and back again. These conditions are far more energetic than the core of any star or even the most powerful particle accelerators we have built. Secondly, it would have been incredibly dense. All the mass and energy of the entire observable universe were packed into this minuscule volume. The density would have been so immense that it would have effectively been infinite, or at least beyond any finite measurement we can conceive. At such extreme densities, the gravitational forces would have been overwhelmingly powerful, bending and warping spacetime in ways that are beyond the descriptive capacity of our current theories. This state is often referred to as a singularity in the context of general relativity. A singularity is a point where the laws of physics, as we currently understand them, break down because they predict infinite values for quantities like density and spacetime curvature. This breakdown signals that general relativity, while incredibly successful for describing gravity on large scales, is incomplete when applied to the very first moments of the universe. It tells us that a more fundamental theory, like a theory of quantum gravity, is needed to accurately describe the cosmic egg. The idea of the cosmic egg is closely linked to the Planck epoch, the earliest period of time in the universe's history, from its beginning up to 10 to the negative 43 seconds, a decimal point followed by 42 zeros and then a 1. During this infinitesimally short time, all 4 fundamental forces of nature — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — are theorized to have been unified into a single superforce. The conditions within the cosmic egg were those of the Planck epoch. It represents the ultimate starting point from which everything else emerged. The expansion from this cosmic egg is what we call the Big Bang. It is crucial to understand that the Big Bang was not an explosion into existing space, but rather the rapid expansion of space itself from this incredibly dense and hot state. As space expanded, it carried the matter and energy with it, causing the universe to cool and dilute. This cooling allowed fundamental particles to eventually form, then atomic nuclei, and later neutral atoms. Over billions of years, gravity then pulled these atoms together to form stars, galaxies, and the large-scale structures we observe today. While we cannot directly observe the cosmic egg, the Big Bang model, which describes the universe expanding from this initial state, is supported by several strong pieces of evidence. One is the ongoing expansion of the universe, first observed by Edwin Hubble in the 1920s. Another is the cosmic microwave background radiation, a faint glow of microwave light permeating the entire universe, which is understood as the leftover heat from the incredibly hot, dense early universe, like the afterglow of the cosmic egg. A third piece of evidence is the cosmic abundance of light elements such as hydrogen, helium, and lithium, which matches the predictions for their formation during the first few minutes after the Big Bang, when the universe was still incredibly hot and dense, essentially expanding out of the cosmic egg state. The theoretical nature of the singularity, or the cosmic egg, highlights the limits of our current scientific understanding. Physicists continue to develop theories such as string theory and loop quantum gravity to provide a more complete description of this initial state, hoping to resolve the paradoxes of infinite density and temperature. Some theories propose that the cosmic egg might have emerged from a quantum foam or a higher dimensional space, or perhaps it was the result of a bounce from a previous contracting universe. Regardless of its exact pre-origin, the cosmic egg remains the conceptual starting point of our universe's grand evolutionary tale, representing the point of maximal compression and energy from which all existence unfolded. The universe we inhabit today is immense, spanning billions of light years and containing countless galaxies, each with hundreds of billions of stars. It is so vast that our minds struggle to fully comprehend its scale. Yet, according to the prevailing scientific models, this entire cosmos, including all the matter, energy, space, and time, originated from something incredibly, almost unimaginably small. This initial state was not just small in comparison to the current universe. It was minuscule on a scale far beyond our everyday experience, fundamentally challenging our understanding of what size even means. At its very first moments, the universe is theorized to have been confined to a volume far smaller than an atom. In fact, theoretical physics suggests it was concentrated into a region smaller than the Planck length, which is approximately 1.6 times 10 to the negative 35 meters, a decimal point followed by 34 zeros and then a 16. This Planck length is not just an arbitrary small number, it represents the scale at which the quantum effects of gravity become significant, and our current laws of physics, particularly general relativity, are expected to break down. Below this scale, the very concepts of continuous space and time may cease to apply in their familiar forms. This means the universe did not merely exist as a tiny object in space. Rather, space itself, along with time, was contained within or emerged from this infinitesimally small volume. This initial condition is often referred to as a singularity within the framework of general relativity. A singularity is a point where the density of matter and the curvature of spacetime become infinite, leading to a situation where the equations of physics yield undefined results. While a useful mathematical concept, it is understood by physicists that such an infinite density points to the limits of general relativity and highlights the necessity of a more complete theory, known as quantum gravity, to describe this earliest phase. The tiny start of the universe was a state where the fundamental nature of reality was governed by the laws of quantum mechanics, but in an extreme gravitational regime. To grasp the implications of such a tiny start, consider that this minuscule volume contained all the fundamental ingredients that would eventually expand and evolve into everything we observe today. This implies an unfathomable concentration of energy. The density of energy within this tiny start would have been extraordinary, far exceeding that found in the core of a star or even within a black hole. In this state, matter as we know it, composed of protons, neutrons and electrons, could not exist. The energy was so immense that any particles would immediately be converted into radiation and then back into other particles in a continuous dynamic process. All the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, are thought to have been unified into a single superforce at this extreme scale. The universe's initial tininess is critical to the Big Bang model. If the universe had started significantly larger, its subsequent expansion and evolution would have been vastly different. The cooling and formation of particles and structures depend directly on the initial high density and temperature, which are a direct consequence of starting from an incredibly small volume. The uniform distribution of matter and radiation observed in the early universe, as evidenced by the cosmic microwave background radiation, also points to an origin from a state where all parts were in close contact, allowing them to reach a consistent temperature. What caused the universe to exist in this tiny, dense state? While the Big Bang theory describes the expansion from this state, it does not fully explain what preceded it, or what caused it to come into being. However, some theoretical ideas from quantum physics offer possible insights. Quantum mechanics permits for the spontaneous appearance of particles and energy even in a vacuum. This concept, known as quantum fluctuations, suggests that even a truly empty vacuum is not inert, but is a bubbling sea of temporary particle-antiparticle pairs. Extending this idea, some theories propose that the universe itself might have emerged from a quantum fluctuation in a pre-existing quantum vacuum, or a quantum foam, a chaotic space-time fabric at the Planck scale. In this view, the tiny start could be seen as a quantum event, a probabilistic emergence from a deeper, more fundamental quantum realm. The sheer scale transformation from this tiny beginning to the colossal universe we observe today is a central theme of cosmology. The universe underwent a period of incredibly rapid expansion, known as cosmic inflation, almost immediately after its tiny start. During this inflationary epoch, which lasted for only a tiny fraction of a second, the universe grew exponentially, from being smaller than a subatomic particle to macroscopic sizes, even potentially larger than a grapefruit in an instant. This dramatic increase in size accounts for many of the universe's observed properties, such as its overall flatness and the uniformity of the cosmic microwave background. Even after inflation, the universe continued to expand, though at a much slower rate, steadily growing over billions of years to its present enormous dimensions. The concept of a tiny start fundamentally challenges our intuitive understanding of space and reality. It forces us to acknowledge that the universe began in a state where familiar concepts like length, time, and even the distinct forces of nature did not apply. It emphasizes that the universe was not a fixed canvas on which events unfolded, but was, from its very beginning, a dynamic and evolving entity, emerging from a state of unimaginable compression and energy into the vast and complex cosmos we explore today. This initial minuscule size holds the key to understanding the subsequent grand unfolding of all cosmic history. The term Big Bang is perhaps the most widely recognized concept in cosmology, yet it is often misunderstood. It does not describe an explosion in space, but rather the rapid expansion of space itself, marking the beginning of our universe as we know it. This pivotal moment refers to the earliest discernible state of the cosmos and the subsequent expansion that led to the formation of everything we observe. The scientific idea of the Big Bang was first put forth in 1927 by Georges Lemaitre, a Belgian priest and physicist who proposed that the universe began from a single, primeval atom, or cosmic egg, that expanded. His theoretical work was soon supported by observational evidence in 1929, when American astronomer Edwin Hubble discovered that galaxies are generally moving away from us and the farther away they are, the faster they are receding. This systematic recession of galaxies, known as Hubble's law, suggested that the universe is expanding, and if it is expanding, then in the past it must have been much smaller and denser. Extrapolating this expansion backward in time leads to the incredibly hot and dense initial state, the Big Bang moment. At this fundamental moment, which is more accurately understood as an epoch rather than a single instant, the universe was contained within an infinitesimally small volume. It was not expanding into pre-existing empty space, as if space were a vast empty room. Instead, space itself, along with time, matter, and energy, began to exist and expand from this ultra-compressed state. This means there was no center to the Big Bang in the conventional sense, no specific point from which everything exploded outwards. Every point in the early universe was effectively the center of the expansion, as space was expanding uniformly everywhere. Immediately following this Big Bang moment, the universe was a super-hot, incredibly dense soup of fundamental particles and radiation. The temperature was so immense, trillions of degrees Celsius and beyond, that ordinary matter could not form. Atoms composed of a nucleus and electrons were impossible. Even atomic nuclei made of protons and neutrons could not exist in a stable form. Instead, the universe was filled with a plasma of quarks, leptons, such as electrons and neutrinos, and their antimatter counterparts, along with a dense sea of photons, light particles. All these particles were constantly colliding and interconverting from energy to matter and back again, as described by Einstein's famous equation E equals mc squared, where energy and mass are interchangeable. In the first tiny fractions of a second after the Big Bang, the fundamental forces of nature, which are distinct today, are believed to have been unified. As the universe began its rapid expansion and started to cool, these forces froze out, or separated from the unified superforce. Gravity was the first to separate, followed by the strong nuclear force, which binds quarks together to form protons and neutrons. Later, the electroweak force separated into the electromagnetic force and the weak nuclear force. This sequence of force separations played a crucial role in shaping the early universe. Within the first minute or so after the Big Bang, as the universe continued to expand and cool, conditions became suitable for the formation of the first atomic nuclei. This process is known as Big Bang nucleosynthesis. Protons and neutrons, which had formed from the quark gluon plasma, began to combine to form the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. This process stopped after about 3 minutes because the universe had expanded and cooled too much for nuclear fusion reactions to continue. The precise observed cosmic abundances of these light elements today, roughly 75% hydrogen, 25% helium, and tiny amounts of lithium by mass, serve as powerful evidence supporting the Big Bang model. Another crucial piece of evidence for the Big Bang is the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons to combine with the nuclei of hydrogen and helium to form stable, neutral atoms. Before this time, the universe was a hot, opaque plasma where photons were constantly scattered by free electrons. Once neutral atoms formed, the photons were no longer scattered and could travel freely through space. This event is called recombination, or decoupling. These photons, having travelled across the universe for billions of years, are what we detect today as the cosmic microwave background. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, this faint uniform microwave radiation comes from every direction in space and has a temperature of approximately 2.7 Kelvin, about negative 270 degrees Celsius, precisely as predicted by Big Bang theory. The tiny temperature variations within this background radiation are also critical, as they represent the initial seeds from which all large-scale structures like galaxies eventually grew. While the Big Bang theory successfully describes the evolution of the universe from a hot, dense state, it does not explain what caused the Big Bang or what, if anything, existed before it. It also faces challenges in explaining certain properties of the universe, such as its remarkable flatness and the uniformity of the cosmic microwave background across regions that could not have been in causal contact. These challenges led to the development of the theory of cosmic inflation, which proposes an even earlier hyper-rapid expansion phase, building upon the foundational idea of the Big Bang moment. Despite these open questions, the Big Bang theory remains the most robust and widely accepted scientific framework for understanding the origin and evolution of our universe. The Big Bang theory posits that our universe began from an incredibly hot and dense state, which then underwent a continuous expansion. However, the initial phase of this expansion was not a steady, gradual process. Instead, cosmological models suggest a period of extraordinarily rapid and exponential growth, far exceeding the current expansion rate known as cosmic inflation. This epoch of rapid expansion occurred in the first fleeting moments of the universe, shaping its fundamental properties and addressing several puzzles left unsolved by the standard Big Bang model alone. The concept of cosmic inflation was first proposed in 1980 by physicist Alan Guth. He developed this theory to address certain problems that arose from the standard Big Bang model, particularly the flatness problem and the horizon problem. The flatness problem asks why the universe's geometry appears so remarkably flat on large scales, meaning that space is not significantly curved in either a spherical or saddle-like manner. The horizon problem asks why the cosmic microwave background radiation, the afterglow of the Big Bang, has such a uniform temperature across vast regions of the sky that, according to the standard Big Bang model, could never have been in causal contact, i.e., light signals would not have had enough time to travel between them to equalize their temperatures. Inflation proposes that the universe underwent an enormous growth spurt during an incredibly short period, specifically from about 10 to the negative 36 seconds, a decimal point followed by 35 zeros and then a 1, after the Big Bang to roughly 10 to the negative 32 seconds. To put this in perspective, this entire period of hyper-rapid expansion lasted for only about 100 trillionth of a trillionth of a trillionth of a second. Within this minuscule time frame, the universe is theorized to have expanded by an enormous factor, at least 10 to the power of 26, and possibly as much as 10 to the power of 100. This means that a region of space that was once smaller than a single proton could have stretched to a size larger than a grapefruit in that incredibly short duration. If the entire observable universe began as a tiny speck, inflation stretched it to its vast current size. What caused this explosive growth? Inflation theory suggests that this rapid expansion was driven by a hypothetical field, often called the inflaton field. This field is a type of scalar field, similar in concept to the Higgs field, which is responsible for giving particles mass. During the inflationary epoch, the inflaton field was in a high-energy state and had a peculiar property. Its energy density remained nearly constant even as space expanded. This constant energy density effectively acted like a repulsive gravitational force, pushing space apart at an accelerating rate. This negative pressure, characteristic of the inflaton field, generated the exponential expansion, causing space to double in size repeatedly in extremely short intervals. The rapid expansion of cosmic inflation successfully resolves the flatness and horizon problems. For the flatness problem, consider a small, wrinkled balloon. If you inflate it to an enormous size, any small wrinkles on its surface will become incredibly smooth and flat on a local scale. Similarly, inflation stretched any initial curvature of the universe so immensely that it became indistinguishable from a perfectly flat geometry over the observable cosmos. For the horizon problem, inflation explains the observed uniformity of the cosmic microwave background by proposing that the regions that appear causally disconnected today were, in fact, in causal contact before inflation. They were part of a much smaller region that reached thermal equilibrium. Inflation then stretched these regions far apart, but their uniform temperature was preserved. Inflation also solves the monopole problem, which addressed the absence of highly energetic magnetic monopoles predicted by some grand unified theories. Inflation would dilute these hypothetical particles to undetectable levels across the vast expanded universe. At the end of the inflationary period, the inflaton field is thought to have decayed or rolled down to a lower energy state. As it did so, its enormous energy was released, converting into a hot, dense soup of ordinary matter and radiation. This event is called reheating and marks the transition from the cold, rapidly expanding inflationary phase to the hot, dense initial conditions of the standard Big Bang model. In essence, inflation provided the initial conditions for the Big Bang as we typically describe it, effectively setting the stage for the formation of particles, atoms, stars, and galaxies. Beyond solving these cosmological puzzles, inflation also provides a mechanism for the origin of the large-scale structure of the universe. During the inflationary period, tiny quantum fluctuations, which are inherent uncertainties in energy and matter at the subatomic level, would have been stretched to macroscopic and then cosmic scales. These stretched quantum fluctuations became slightly denser and slightly emptier regions in the otherwise smooth early universe. Over billions of years, these tiny density variations acted as gravitational seeds, slowly pulling in more matter and eventually growing into the galaxies, galaxy clusters, and vast cosmic structures we observe today. The precise pattern of these variations, as measured by satellites observing the cosmic microwave background, such as WMAP and Planck, strongly matches the predictions of inflationary theory, providing key observational support. While cosmic inflation remains a theoretical framework, and its precise mechanism is still an active area of research, its remarkable success in explaining key features of the universe has made it a central pillar of modern cosmology. It illustrates how an incredibly rapid and fleeting expansion in the earliest moments could have transformed a tiny quantum realm into the vast structured cosmos we inhabit, setting the stage for all subsequent cosmic evolution. The standard Big Bang model describes the universe expanding from an incredibly hot and dense state, evolving over billions of years into the cosmos we observe today. However, this standard model, while remarkably successful, faced several significant challenges in the late 20th century. These challenges led to the development of a crucial extension, the theory of cosmic inflation. Inflation proposes a period of extremely rapid, exponential expansion that occurred in the very first fraction of a second after the Big Bang, fundamentally shaping the universe's large-scale properties. One of the main problems inflation sought to solve was the flatness problem. Observations indicate that the universe's geometry on large scales is remarkably flat, meaning that space is not significantly curved like the surface of a sphere or a saddle. In the absence of inflation, the standard Big Bang model predicted that the universe should have quickly curved either positively or negatively, unless its initial density was tuned to an incredibly precise value. Any tiny deviation from this perfect balance would have led to a universe that either collapsed rapidly or expanded so quickly that no structures could form. Inflation elegantly resolves this by stretching any initial curvature to such an enormous extent that the observable universe appears perfectly flat, much like a small patch on the surface of an incredibly inflated balloon appears flat to an ant living on it. Another significant issue was the horizon problem. The cosmic microwave background radiation, a faint glow of microwaves permeating the entire sky, is incredibly uniform in temperature across vast regions. These regions are so far apart that, according to the standard Big Bang model, light would not have had enough time to travel between them since the universe began. This means they could not have exchanged information or reached thermal equilibrium. Yet, their temperatures are almost identical. Inflation solves this by proposing that these regions were, in fact, in causal contact before inflation. They were part of a much smaller pre-inflationary patch that was able to homogenize its temperature. Inflation then stretched this tiny uniform patch to an immense size, pushing these regions far apart while preserving their initial temperature uniformity. A third problem addressed by inflation is the monopole problem. Some theories that attempt to unify the fundamental forces of nature predict the existence of extremely heavy, stable particles called magnetic monopoles, which would have been produced in abundance in the very early, hot universe. However, despite extensive searches, no such monopoles have ever been detected. Inflation provides a solution by diluting these hypothetical particles to such an extremely low density across the vast expanded universe that the probability of encountering one becomes negligible. The inflationary epoch is theorized to have occurred incredibly early, typically from about 10 to the negative 36 seconds, a decimal point followed by 35 zeros and then a 1, after the Big Bang to roughly 10 to the negative 32 seconds. This means the entire period of hyper-rapid expansion lasted for only about 100 trillionth of a trillionth of a trillionth of a second. Within this fleeting moment, the universe underwent an astonishing increase in size, expanding by a factor of at least 10 to the power of 26, and possibly much more, perhaps up to 10 to the power of 100. To illustrate this scale, a region of space that was initially smaller than a single proton could have grown to be larger than a grapefruit, or even much larger, in this incredibly short duration. The mechanism driving this rapid expansion is attributed to a hypothetical field known as the inflaton field. This is a type of scalar field, similar in concept to the Higgs field, which is responsible for giving particles mass. During the inflationary period, the inflaton field was in a high-energy state. Unlike ordinary matter or radiation, the energy density of this inflaton field remained nearly constant even as space expanded. This constant energy density effectively created a repulsive gravitational force, generating a tremendous negative pressure that pushed space apart at an accelerating exponential rate. This unique property of the inflaton field allowed the universe to double in size repeatedly and incredibly quickly, leading to the dramatic expansion. At the end of the inflationary period, the inflaton field is thought to have decayed or rolled down from its high-energy state to a lower, more stable energy configuration. As it did so, its vast potential energy was released, converting into a hot, dense plasma of ordinary matter and radiation. This event is called reheating, and effectively marks the transition from the cold, rapidly expanding inflationary phase to the hot, dense initial conditions of the standard Big Bang model. In essence, inflation provided the initial conditions for the Big Bang as we typically describe it, setting the stage for all subsequent cosmic evolution, including the formation of fundamental particles, atomic nuclei, and eventually stars and galaxies. Beyond solving the flatness, horizon, and monopole problems, inflation also provides a compelling explanation for the origin of the large-scale structure we observe in the universe today. During the inflationary period, tiny quantum fluctuations, which are inherent uncertainties in energy and matter at the subatomic level, would have been stretched to macroscopic and then cosmic scales. These stretched quantum fluctuations became slightly denser and slightly emptier regions in the otherwise smooth early universe. Over billions of years, these minute density variations acted as gravitational seeds, slowly pulling in more matter and eventually growing into the galaxies, galaxy clusters, and vast cosmic structures that form the cosmic web. The precise pattern of these variations, observed as tiny temperature differences in the cosmic microwave background radiation by missions like WMAP and Planck, provides strong observational support for the inflationary paradigm. While cosmic inflation remains a theoretical framework, and the precise nature of the inflaton field is still an active area of research, its remarkable success in explaining several key features of the universe has made it an indispensable component of modern cosmology. It illustrates how an incredibly rapid and fleeting expansion in the earliest moments could have transformed a tiny quantum realm into the vast structured cosmos we inhabit, setting the stage for all subsequent cosmic evolution and providing the initial conditions for the universe we see around us. Following the incredibly brief but dramatic period of cosmic inflation, the universe entered a new phase of its existence. This chapter focuses on the events that unfolded within the first few seconds after the Big Bang, a period of rapid cooling and fundamental particle formation that laid the groundwork for all subsequent cosmic evolution. This era, stretching from roughly 10 to the negative 12 seconds to a few minutes after the Big Bang, was characterized by extreme temperatures and densities, but conditions were rapidly changing. Immediately after the end of inflation and the reheating process, the universe was filled with an incredibly hot and dense plasma. The temperature was still immense, in the range of trillions of degrees Celsius. At these energies, the fundamental forces of nature, which had been unified during the Planck epoch and the inflationary period, continued to separate. The electroweak force, which had been unified, split into the electromagnetic force and the weak nuclear force at about 10 to the negative 12 seconds after the Big Bang. This separation of forces allowed for distinct interactions between particles, setting the stage for the formation of more complex structures. In this super-hot, dense environment, matter as we know it could not yet exist in stable forms like atoms or even atomic nuclei. Instead, the universe was a chaotic soup of elementary particles. These included quarks, the fundamental building blocks of protons and neutrons, leptons such as electrons and neutrinos, and force-carrying particles like photons, light particles, and gluons, which bind quarks together. Particles and their antimatter counterparts were constantly being created from pure energy and then annihilating each other, converting back into energy, following Einstein's principle of mass-energy equivalence. As the universe continued to expand, it also cooled very rapidly. This cooling was crucial because it allowed for the formation of more stable particles. At about 10 to the -6 seconds, 1/1,000,000th of a second, after the Big Bang, the universe had cooled sufficiently for quarks to bind together under the influence of the strong nuclear force. This process, known as hadronization, led to the formation of protons and neutrons, the particles that make up the nuclei of atoms. For every proton and neutron that formed, there was also an antiproton and antineutron. A critical event during this period was the slight imbalance between matter and antimatter. For every billion antimatter particles, there was approximately 1,000,000,001 matter particles. As the universe continued to cool, the vast majority of matter and antimatter particles annihilated each other, releasing a tremendous amount of energy in the form of photons. However, because of that tiny excess of matter, a small residue of matter particles survived. This surviving matter, representing only about 1 part in a billion of the original particle-antiparticle pairs, is what constitutes all the matter in the universe today, including ourselves, stars, and galaxies. Without this minute asymmetry, the universe would have been filled only with radiation, with no stable matter to form anything. The precise reason for this matter-antimatter asymmetry is one of the enduring mysteries in physics. By about 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Celsius. At this point, neutrinos, which are very light and weakly interacting particles, decoupled from the rest of the matter and radiation. They began to travel freely through space, forming a cosmic neutrino background, similar to the cosmic microwave background but much harder to detect. The most significant event within the first few minutes after the Big Bang was Big Bang nucleosynthesis, BBN. This process, occurring roughly from about 1 minute to 3 minutes after the Big Bang, saw the formation of the first light atomic nuclei. As the universe cooled further, to about 1 billion degrees Celsius, protons and neutrons could finally combine to form stable atomic nuclei. Protons, being hydrogen nuclei, were already abundant. Neutrons combined with protons to form deuterium, heavy hydrogen, which then fused to create helium-4 nuclei. Trace amounts of lithium-7 were also produced. This nuclear fusion process was possible only during this brief window, because the universe was hot and dense enough for fusion reactions to occur, but also expanding and cooling rapidly enough to prevent all the hydrogen from fusing into heavier elements. The BBN process effectively stopped after about 3 minutes, because the universe had expanded and cooled too much. The density dropped, and the temperature became too low to sustain the nuclear fusion reactions necessary to build heavier nuclei. This left the universe with a primordial composition consisting of approximately 75% hydrogen and 25% helium by mass, along with tiny traces of lithium. These predicted abundances are one of the most powerful pieces of evidence supporting the Big Bang model. Observations of the oldest, most pristine gas clouds in the universe, which have not been significantly altered by stellar processes, show precisely these proportions of light elements, providing a strong confirmation of the conditions in the universe's first few minutes. After these first few minutes, the universe continued to expand and cool, but no further significant nuclear reactions occurred for hundreds of thousands of years. The universe remained a hot, opaque plasma for a long period, waiting for conditions to become suitable for the formation of the first neutral atoms, which would eventually lead to the release of the cosmic microwave background radiation and the subsequent formation of stars and galaxies. The events of these first few seconds were therefore absolutely critical, setting the stage for the entire cosmic drama that followed. In its very earliest moments, immediately after the period of cosmic inflation and the subsequent reheating, the universe existed in a state fundamentally different from anything we can observe today. It was not a void, nor was it filled with stars and galaxies. Instead, it was a superhot soup of elementary particles and radiation, a plasma so dense and energetic that matter and energy were constantly interconverting, and the fundamental forces of nature were either unified or in the process of separating. This epoch, stretching from the end of inflation, around 10 to the negative 32 seconds, to about the first few minutes after the Big Bang, defines the initial conditions from which everything else evolved. The term superhot soup aptly describes the universe's state because it was a fluid-like mixture where individual particles did not yet exist in stable, distinct forms like atoms. The temperatures were extreme, far beyond anything imaginable on Earth. We are talking about temperatures in the range of trillions, quadrillions, or even quintillions of degrees Celsius. To put this into perspective, the core of our Sun is only about 15 million degrees Celsius. At these incredibly high temperatures, particles moved at nearly the speed of light, constantly colliding with immense energy. In this super-hot environment, the concept of matter and energy being distinct entities was blurred. According to Albert Einstein's famous equation, E equals m squared, energy, E, and mass, m, are interchangeable, with the speed of light squared, c squared, acting as the conversion factor. In the early universe, the energy density was so high that photons, particles of light, could spontaneously convert into particle-antiparticle pairs, and these pairs could then annihilate each other, converting back into photons. This continuous creation and annihilation meant that the universe was a dynamic equilibrium of matter, antimatter, and radiation. There was no stable, enduring matter as we know it. The particles present in this soup were the most fundamental building blocks of matter and force carriers. These included quarks. These are the elementary particles that combine to form protons and neutrons. At these extreme temperatures, quarks were not bound together but existed as a free, unconfined plasma. Leptons. This family includes electrons, muons, taus, and their corresponding neutrinos. Electrons are familiar, but in this early universe they were highly energetic and not bound to any nuclei. Photons. These are particles of light, and were the most abundant particles in the early universe, carrying the vast majority of the universe's energy. The universe was completely opaque to light because photons were constantly scattering off the free charged particles. Gluons. These are the force-carrying particles for the strong nuclear force, which binds quarks together. W and Z bosons. These are the force-carrying particles for the weak nuclear force, responsible for radioactive decay. During this early phase, the fundamental forces of nature were either unified or in the process of separating. At the very highest energies, potentially during the Grand Unified Theory, GUT epoch, before electro-weak separation, the strong, weak, and electromagnetic forces might have been unified into a single, grand unified force. As the universe cooled, these forces froze out or separated, much like steam turning into water and then ice as it cools, each phase transition marking a distinct change in the universe's properties. The electroweak force separated into the electromagnetic and weak forces at about 10 to the negative 12 seconds, and the strong force had already separated earlier. Gravity is believed to have separated even earlier, during the Planck epoch. The universe was in a state of thermal equilibrium, meaning that energy was distributed uniformly throughout, and all particles had roughly the same average energy. This constant interaction and energy exchange ensured that the soup was very smooth and uniform, a crucial initial condition for the subsequent formation of the large-scale structures we see today. Any tiny irregularities or quantum fluctuations that existed were quickly smoothed out due to the rapid interactions and high energies. This superhot soup phase was also the period where the slight imbalance between matter and antimatter became significant. While particles and antiparticles were constantly being created and annihilated, a tiny excess of matter, approximately 1 part in a billion, allowed a small amount of matter to survive the annihilation process as the universe cooled. This surviving matter is what eventually formed all the stars, galaxies, and everything else in the universe. If this tiny asymmetry had not existed, all matter and antimatter would have annihilated, leaving behind a universe composed only of photons and neutrinos. The super-hot soup persisted for only a few minutes. As the universe continued its rapid expansion, it cooled quickly. This cooling was the key driver for subsequent events. Once the temperature dropped sufficiently, around 1/1,000,000th of a second after the Big Bang, quarks could finally bind together to form protons and neutrons. A few minutes later, the temperature had dropped enough for these protons and neutrons to fuse, forming the first light atomic nuclei during Big Bang nucleosynthesis. The transition from this undifferentiated super-hot soup to a universe with distinct particles and eventually atomic nuclei marked a critical step in the universe's journey from absolute nothingness to the complex cosmos we inhabit. In the universe's earliest moments, immediately following the period of cosmic inflation and the subsequent reheating, the cosmos was an incredibly hot and dense environment. This state, often described as a super-hot soup, was so energetic that matter as we know it could not exist in stable, complex forms. Instead, it was a dynamic plasma where energy and matter were constantly interconverting. As the universe underwent rapid expansion, it began to cool, and this cooling was the crucial process that allowed the first fundamental particles, the building blocks of all matter, to emerge and stabilize. The universe began in a state where temperatures were unimaginably high, reaching trillions of degrees Celsius. At these extreme energies, particles were constantly being created from pure energy and then annihilating each other, converting back into energy in a continuous cycle. This was governed by the principle of mass-energy equivalence, where mass and energy are interchangeable. The universe was in a state of thermal equilibrium, meaning that energy was distributed uniformly and particles had roughly the same average energy. There were no distinct stable particles in the way we understand them today. The very first particles to appear were the most elementary ones, the fundamental constituents of matter and the carriers of forces. These are categorized into two main groups: quarks and leptons. Quarks are the building blocks of heavier particles like protons and neutrons, while leptons include familiar particles like electrons and neutrinos. The appearance of these particles was not a sudden singular event, but a gradual process tied directly to the universe's rapid cooling. At temperatures above 10 trillion degrees Celsius, which corresponds to the universe's state at around 10 to the negative 12 seconds, 1/1,000,000th of a second, after the Big Bang, the universe was dominated by a plasma of quarks, leptons, and their antimatter counterparts. At this point, the electromagnetic force and the weak nuclear force were still unified as the electroweak force. As the universe cooled below this temperature, the electroweak force separated into the distinct electromagnetic and weak nuclear forces. This separation was a critical phase transition, allowing for different types of interactions between particles. As the universe continued to expand and cool, its temperature dropped further. A significant event occurred at approximately 10 to the negative 6 seconds, 1/1,000,000th of a second, after the Big Bang, when the temperature had fallen to about 2 trillion degrees Celsius. At this temperature, the strong nuclear force, which had already separated from the other forces, became strong enough to bind quarks together. This process is known as hadronization. Before this point, quarks existed freely in a state called a quark-gluon plasma, where they moved independently, much like molecules in a gas. But as the universe cooled, the strong force confined the quarks into stable composite particles called hadrons. The most important hadrons formed during this period were protons and neutrons. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 1 up quark and 2 down quarks. These are the particles that would eventually form the nuclei of all atoms. For every proton and neutron that formed, an antiparticle, an antiproton or antineutron also formed. This period was characterized by a dynamic balance between the formation of these particles and their annihilation with their antimatter counterparts. Alongside the formation of protons and neutrons, leptons also continued to exist and interact. Electrons, being fundamental particles, did not undergo hadronization. They remained as free individual particles. Neutrinos, which are very light and interact only through the weak nuclear force, also continued to exist. However, as the universe cooled further, at about 1 second after the Big Bang, the temperature dropped to about 10 billion degrees Celsius. At this point, neutrinos decoupled from the rest of the matter and radiation. They stopped interacting frequently with other particles and began to travel freely through space, forming a cosmic neutrino background that exists today, though it is extremely difficult to detect. The formation of stable protons and neutrons was a pivotal step in the universe's evolution. These particles are the building blocks of atomic nuclei, and their existence was a prerequisite for the next major event, nucleosynthesis, the formation of the first light atomic nuclei. Without the prior formation and stabilization of protons and neutrons, the subsequent cosmic processes that led to the formation of elements would not have been possible. The process of particle formation was driven by the universe's continuous expansion and cooling. As the temperature dropped below certain thresholds, the energy available for particle creation diminished. This meant that while particle-antiparticle pairs were still annihilating, new pairs were no longer being created as frequently. This led to a net decrease in the number of particles, as the remaining particles and antiparticles annihilated each other. However, a crucial asymmetry, which will be discussed in detail in the next section, ensured that a small excess of matter particles survived this annihilation, forming the basis for all the matter we observe today. The conditions during these first few seconds were so extreme that they are difficult to replicate in laboratories. However, particle accelerators like the Large Hadron Collider at CERN can recreate energies similar to those present in the universe at about 10 to the negative 12 seconds after the Big Bang. By smashing particles together at incredibly high speeds, physicists can observe the behavior of quarks and gluons in a quark-gluon plasma, providing experimental evidence that supports our theoretical understanding of these early moments. The study of these particle interactions helps to validate the models that describe how the first fundamental particles appeared from the superhot, dense plasma of the early universe. The existence of matter in our universe, from the smallest subatomic particles to the largest galaxies, hinges on a profound cosmic puzzle, the mystery of antimatter. According to fundamental physical laws, whenever a particle is created from energy, its corresponding antiparticle is also created. For example, if a photon, a particle of light, has enough energy, it can spontaneously transform into an electron and a positron, the antimatter counterpart of an electron. Conversely, when a particle and its antiparticle meet, they annihilate each other, converting their entire mass back into energy, typically in the form of photons. This principle of particle-antiparticle creation and annihilation is a cornerstone of quantum field theory and has been confirmed countless times in particle accelerator experiments. In the extremely hot and dense conditions of the very early universe, immediately after the Big Bang and the period of cosmic inflation, the universe was a super-hot soup of energy and particles. Temperatures were so high that particles and antiparticles were constantly being created and destroyed in vast numbers. For every quark, there was an antiquark. For every electron, there was a positron. The universe was in a state of near-perfect symmetry between matter and antimatter. If this symmetry had been absolute, then as the universe expanded and cooled, all the matter and antimatter particles would have annihilated each other, leaving behind a universe filled only with photons and neutrinos, with no stable matter to form stars, planets, or life. However, our universe is clearly dominated by matter. We exist, stars exist, galaxies exist. This observable reality implies that there must have been a slight crucial imbalance in the early universe. For every billion antimatter particles, there was approximately 1,000,000,001 matter particles. This tiny excess of matter, perhaps 1 part in a billion, is what survived the massive annihilation process as the universe cooled. This surviving residue of matter is what makes up everything we see around us today. The antimatter mystery is precisely this. Why was there this tiny yet profoundly significant asymmetry? What mechanism led to this slight excess of matter over antimatter? This phenomenon is known as baryogenesis, for baryons like protons and neutrons, and leptogenesis, for leptons like electrons. It refers to the hypothetical processes that occurred in the very early universe, within the first fraction of a second, which generated this observed asymmetry. For baryogenesis to occur, three conditions known as the Sakharov conditions must be met. These conditions were proposed by Soviet physicist Andrei Sakharov in 1967. First, there must be processes that violate baryon number conservation. Baryon number is a quantity that is conserved in most particle interactions, meaning the total number of baryons, like protons and neutrons, minus the total number of antibaryons remains constant. For a net excess of baryons to be created, processes must exist that can change the baryon number. Second, there must be C-symmetry violation and CP symmetry violation. C-symmetry, charge conjugation symmetry, means that the laws of physics should be the same if all particles are replaced by their antiparticles. CP symmetry, charge parity symmetry, means the laws of physics should be the same if particles are replaced by their antiparticles, and their spatial coordinates are inverted, a mirror image. If these symmetries were perfectly preserved in the early universe, then matter and antimatter would have been created at exactly equal rates, leading to complete annihilation. Therefore, a violation of these symmetries is necessary to produce an imbalance. While small violations of CP symmetry have been observed in laboratories in the decay of certain particles like K mesons and B mesons, these are not large enough to account for the observed matter-antimatter asymmetry in the universe. This suggests that a more significant source of CP violation, perhaps involving new, undiscovered particles or forces, must have been active in the very early universe. Third, the universe must have been out of thermal equilibrium. If the universe remained in perfect thermal equilibrium, any processes that created a matter-antimatter asymmetry would be undone by the reverse processes. Therefore, a period where the universe was expanding and cooling rapidly, preventing particles from reaching equilibrium, is necessary for the asymmetry to freeze in. The rapid expansion during and immediately after inflation would have provided such out-of-equilibrium conditions. Several theoretical models attempt to explain baryogenesis, often involving physics beyond the standard model of particle physics, which is our current best description of fundamental particles and forces. One prominent class of theories involves grand unified theories, GUTs, which propose that at extremely high energies, the strong, weak and electromagnetic forces are unified into a single force. These GUTs often predict the existence of new, very heavy particles, like X and Y bosons, that could decay unequally into quarks and antiquarks, leading to a net baryon number. These decays would occur at extremely high temperatures, characteristic of the very early universe, and would violate baryon number, C-symmetry, and CP symmetry. Another proposed mechanism is electroweak baryogenesis. This theory suggests that the matter-antimatter asymmetry could have been generated during the electroweak phase transition, when the electroweak force separated into the electromagnetic and weak forces at temperatures around 100 billion degrees Celsius. This transition, which occurred about 10 to the negative 12 seconds after the Big Bang, could have provided the necessary out-of-equilibrium conditions and CP violation to create the baryon asymmetry. However, the amount of CP violation within the standard model is insufficient, again pointing to the need for new physics. Leptogenesis is another class of theories that proposes the initial asymmetry was created in the lepton sector, e.g., involving heavy neutrinos, and then later converted into a baryon asymmetry through processes known as sphalerons, which can interconvert lepton and baryon numbers at high temperatures. This mechanism is particularly appealing because it could explain the tiny masses of neutrinos, which are also not fully accounted for by the standard model. The antimatter mystery is not just an academic curiosity, it is fundamental to our very existence. Without this tiny excess of matter, the universe would be a desolate place filled only with radiation, with no possibility for the formation of stars, planets, or life. The fact that we observe a universe dominated by matter is direct evidence that some process, or combination of processes, violated the matter-antimatter symmetry in the very early cosmos. Solving this mystery requires probing physics at extremely high energies, beyond what current particle accelerators can achieve, and is a major goal for future theoretical and experimental research in particle physics and cosmology. Understanding the origin of this asymmetry is crucial for a complete picture of how our universe came to be. The universe's journey from an incredibly hot and dense initial state to the vast complex cosmos we observe today is fundamentally a story of continuous cooling. This cooling was not merely a passive consequence of expansion, it was the active driver of every major phase transition and the formation of increasingly complex structures, from elementary particles to atoms and eventually stars and galaxies. The universe's expansion caused its temperature to drop, and each drop in temperature allowed new physical processes to occur, fundamentally changing the universe's composition and behavior. Immediately after the end of cosmic inflation and the reheating process, the universe was a super-hot soup of fundamental particles and radiation. The temperature was unimaginably high, reaching quadrillions of degrees Celsius. At these extreme temperatures, particles were moving at relativistic speeds, constantly colliding and interconverting from energy to matter and back again. The universe was essentially a plasma where no stable, composite particles could exist. As the universe expanded, the volume it occupied increased, and the energy density within that volume decreased. This decrease in energy density manifested as a drop in temperature. Think of a gas expanding. As it expands, its particles spread out, collide less frequently, and lose kinetic energy, resulting in a drop in temperature. The universe behaved similarly, but on a cosmic scale. The first significant cooling event allowed the fundamental forces of nature to separate. At the highest temperatures, it is theorized that all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. As the universe cooled, gravity was the first to freeze out or separate, followed by the strong nuclear force. Later, at around 10 to the negative 12 seconds, 1/trillionth of a second, after the Big Bang when the temperature had dropped to about 10 trillion degrees Celsius, the electroweak force separated into the distinct electromagnetic and weak nuclear forces. Each of these separations marked a phase transition, fundamentally altering how particles interacted and setting the stage for the formation of matter. A crucial cooling threshold was reached at approximately 10 to the negative 6 seconds, 1/millionth of a second, after the Big Bang when the temperature had fallen to about 2 trillion degrees Celsius. At this point, the universe had cooled sufficiently for quarks to bind together under the influence of the strong nuclear force. This process, known as hadronization, led to the formation of protons and neutrons, the particles that make up atomic nuclei. Before this, quarks existed freely in a quark-gluon plasma. The cooling provided the necessary conditions for these fundamental building blocks to coalesce into stable composite particles. As the universe continued to cool, another critical event occurred: the annihilation of matter and antimatter. In the superhot soup, particles and antiparticles were constantly being created and destroyed. However, as the temperature dropped, the energy available for creating new particle-antiparticle pairs diminished. This meant that annihilation became dominant. The vast majority of matter and antimatter particles annihilated each other, releasing a tremendous amount of energy in the form of photons. Due to a tiny, crucial asymmetry, as discussed in the antimatter mystery chapter, a small residue of matter particles survived this annihilation. This residual matter, representing only about 1 part in a billion of the original particle-antiparticle pairs, is what constitutes all the matter in the universe today. This process was largely complete by about 1 second after the Big Bang, when the temperature had dropped to about 10 billion degrees Celsius. The next major cooling-driven event was Big Bang nucleosynthesis, BBN, which occurred roughly from about 1 minute to 3 minutes after the Big Bang. By this time, the universe had cooled to approximately 1 billion degrees Celsius. This temperature was still hot enough for protons and neutrons to fuse, but cool enough for them to form stable nuclei without immediately being broken apart by high-energy photons. During BBN, protons and neutrons combined to form the nuclei of the lightest elements: hydrogen, single protons; deuterium, 1 proton and 1 neutron; helium-3, 2 protons and 1 neutron; helium-4, 2 protons and 2 neutrons; and trace amounts of lithium-7. This process ceased after about 3 minutes because the universe had expanded and cooled too much, making it too dilute and too cold for further nuclear fusion reactions to occur. The precise cosmic abundances of these light elements observed today are a powerful confirmation of the universe's cooling history during these first few minutes. After BBN, the universe entered a period known as the Dark Ages. For the next 380,000 years, the universe continued to expand and cool, but no significant new structures formed. The temperature gradually dropped from about 1 billion degrees Celsius to approximately 3,000 degrees Celsius. During this long period, the universe was still a hot, opaque plasma. Electrons were free and not bound to atomic nuclei, and they constantly scattered photons, preventing light from travelling freely. The final major cooling event in the early universe was recombination, or decoupling, which occurred about 380,000 years after the Big Bang. At this point, the universe had cooled to about 3,000 degrees Celsius. This temperature was low enough for electrons to finally combine with the nuclei of hydrogen and helium to form stable, neutral atoms. Once electrons were bound to nuclei, the universe became transparent to light. Photons, which had been constantly scattering off free electrons, were now free to travel unimpeded through space. These photons, having travelled across the universe for billions of years, are what we detect today as the cosmic microwave background radiation. The release of this light marked the end of the Dark Ages and provided a direct snapshot of the universe when it was still very young, confirming its cooling history. From this point onward, the universe continued to cool, though at a much slower rate. This continued cooling and expansion allowed gravity to begin its long work of pulling together the slight density fluctuations that existed in the early universe, eventually leading to the formation of the first stars, galaxies, and the large-scale cosmic structures we observe today. The entire cosmic evolution is a testament to the profound impact of the universe's continuous cooling, driven by its relentless expansion. The universe we inhabit is governed by a set of fundamental interactions that dictate how particles behave and how structures form. These are known as the fundamental forces of nature. In our current understanding, there are 4 such forces: gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Each has distinct properties, strengths, and ranges, governing everything from the orbits of planets to the decay of radioactive elements. However, the prevailing scientific theories suggest that in the extreme conditions of the very early universe, these seemingly distinct forces were not always separate. Instead, they were once unified, acting as different manifestations of a single, more fundamental force. The story of the universe's origin is, in part, the story of how these forces took shape, separating and defining themselves as the cosmos expanded and cooled. The concept of force unification is a central theme in modern physics, aiming to describe all fundamental interactions within a single theoretical framework. This idea stems from the observation that at very high energies, the distinctions between forces become blurred. For instance, the electromagnetic force and the weak nuclear force, while appearing very different in our everyday world, are known to unify into a single electro-weak force at energies achievable in powerful particle accelerators. Extending this idea, physicists hypothesize that at even higher energies, characteristic of the universe's earliest moments, the strong nuclear force might also unify with the electroweak force into a grand unified force. And at the very highest energies, potentially even gravity could join this grand unification, leading to a theory of everything. The separation of these forces occurred in a specific sequence, driven by the continuous cooling of the universe as it expanded rapidly after the Big Bang. This process can be thought of as a series of phase transitions, similar to how water vapor cools to become liquid water and then freezes to become ice. Each phase transition in the early universe marked a point where a unified force broke symmetry and split into distinct forces, each with its own unique characteristics. The very first force to separate from a hypothetical unified superforce is believed to have been gravity. This separation would have occurred at the earliest conceivable moment of the universe, during what is known as the Planck epoch. This epoch spans from the beginning of time, or the earliest meaningful moment, up to approximately 10 to the negative 43 seconds, a decimal point followed by 42 zeros and then a 1. At this incredibly tiny fraction of a second, the universe was unimaginably hot and dense, with temperatures reaching 10 to the power of 32 degrees Celsius. At such extreme conditions, all four fundamental forces are thought to have been unified into a single, indivisible superforce, or to have been operating under the laws of quantum gravity, a theory still under development. As the universe expanded and cooled just slightly from this ultimate extreme, gravity is theorized to have decoupled or separated from the other unified forces. This made gravity a distinct force, influencing the large-scale structure of the universe from its very inception. The precise mechanism of this separation is still a subject of intense research within the realm of quantum gravity, as our current theories are incomplete at this fundamental level. Following gravity's emergence, the next major force separation involved the strong nuclear force. This force is responsible for binding quarks together to form protons and neutrons, and for holding these protons and neutrons together within atomic nuclei, at energies characteristic of the grand unified theory, GUT epoch, which occurred between 10 to the negative 43 seconds and 10 to the negative 36 seconds after the Big Bang. The strong force is theorized to have been unified with the electroweak force. As the universe continued to expand and cool below a certain energy threshold, around 10 to the power of 29 degrees Celsius, the strong force froze out from the unified grand unified force. This separation meant that the strong force became a distinct interaction, operating independently. The precise timing and mechanism of this GUT symmetry breaking are still theoretical, as the energies involved are far beyond what can be replicated in any laboratory. However, the separation of the strong force was crucial because it paved the way for the formation of stable protons and neutrons later in the universe's history. The final major unification to break was the electroweak force. This force, as its name suggests, is a unification of the electromagnetic force and the weak nuclear force. At temperatures above approximately 10 trillion degrees Celsius, which corresponds to the universe's state at around 10 to the negative 12 seconds, 1/trillionth of a second, after the Big Bang, these two forces were indistinguishable. They acted as a single force, mediated by a set of particles including photons for electromagnetism and W and Z bosons for the weak force. As the universe continued to expand and cool below this critical temperature, the electroweak force broke symmetry, separating into the distinct electromagnetic and weak nuclear forces we observe today. This phase transition is well understood and has been experimentally verified in particle accelerators like CERN's Large Hadron Collider, where physicists can recreate energies high enough to observe the unified electroweak force. The separation of these forces was vital for the subsequent formation of atoms and the processes of radioactive decay. The sequential separation of these fundamental forces as the universe cooled was not just a theoretical curiosity, it had profound consequences for the evolution of the cosmos. Each separation allowed new types of particles to form and new interactions to dominate, fundamentally changing the universe's composition and behavior. The emergence of distinct forces meant that particles could begin to interact in specific ways, leading to the formation of stable protons and neutrons, then atomic nuclei, and eventually neutral atoms. Without this precise sequence of force separations dictated by the universe's cooling expansion, the universe would not have developed the structures and complexity necessary for stars, galaxies, and ultimately, life itself. The taking shape of these forces was thus a foundational chapter in the universe's grand story. Among the four fundamental forces of nature, gravity holds a unique and profound position, especially when considering the very beginning of the universe. Unlike the other forces, which govern interactions at the subatomic level, gravity is the dominant force on the larger scales, shaping the structure of galaxies, clusters, and the universe as a whole. Its emergence as a distinct force marks the earliest known phase transition in the cosmos, setting the stage for all subsequent cosmic evolution. In our current understanding, gravity is not merely a force that pulls objects together, but rather a manifestation of the curvature of space-time itself. According to Albert Einstein's theory of general relativity, massive objects warp the fabric of space-time around them, and what we perceive as gravitational attraction is simply objects following the curves in this warped space-time. This geometric description of gravity makes it fundamentally different from the other three forces, which are described by quantum field theories involving the exchange of force-carrying particles. The emergence of gravity as a distinct force is theorized to have occurred at the very earliest moments of the universe, during what is known as the Planck epoch. This epoch is an unimaginably brief period, lasting from the absolute beginning of time, or the earliest meaningful moment, up to approximately 10 to the negative 43 seconds, a decimal point followed by 42 zeros and then a 1. At this extreme point, the universe was compressed into an infinitesimally small volume, smaller than the Planck length, about 1.6 times 10 to the negative 35 meters, and its temperature was an astounding 10 to the power of 32 degrees Celsius. At such extreme energies and densities, all four fundamental forces, gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force, are believed to have been unified into a single, indivisible superforce. This is the realm where quantum gravity, a theoretical framework that aims to reconcile general relativity with quantum mechanics, would be necessary to describe the universe. Our current theories of physics, including general relativity, break down at the Planck scale, indicating that a more fundamental description is needed for this earliest phase. As the universe expanded and cooled ever so slightly from this ultimate extreme, gravity is theorized to have decoupled or frozen out from the unified superforce. This means that gravity became a distinct interaction, separate from the other forces. The precise mechanism of this separation is still a subject of intense theoretical research, as it requires a complete theory of quantum gravity, which has not yet been fully developed. However, the idea is that as the universe's energy density dropped below a certain threshold, the conditions that kept all forces unified no longer existed, and gravity emerged as an independent entity. Once gravity emerged as a distinct force, its role in the shaping of the early universe became paramount. Even though it is the weakest of the four fundamental forces at the particle level, its influence extends over infinite distances, and it is always attractive. This makes it the dominant force on large scales. Immediately after its separation, gravity began to act on the tiny quantum fluctuations that existed in the very early universe. These fluctuations, which were inherent uncertainties in the energy and matter distribution at the subatomic level, were stretched to macroscopic and then cosmic scales during the period of cosmic inflation. These stretched quantum fluctuations became the initial seeds for all the large-scale structures we observe today. Gravity began to pull together the slightly denser regions of matter and energy, while the slightly emptier regions became even less dense. Over billions of years, these tiny initial variations, amplified by gravity, grew into the vast cosmic web of galaxies, galaxy clusters and superclusters, separated by immense voids. Without gravity's early emergence and its long-range attractive nature, the universe would have remained a uniform, featureless expanse with no stars or galaxies to form. Gravity also played a crucial role in the overall expansion of the universe. While the initial rapid expansion of inflation was driven by the inflaton field, after inflation ended, gravity began to act as a braking force, slowing down the expansion. The interplay between the initial expansion energy and the gravitational pull of all the matter and energy in the universe determined the ultimate fate of the cosmos. For billions of years, gravity worked to pull matter together, forming structures, while the overall expansion continued to stretch space apart. Furthermore, gravity was responsible for the initial compression of all matter and energy into the cosmic egg, or singularity from which the Big Bang is thought to have originated. The immense gravitational pull at that point was so strong that it compressed everything into an infinitesimally small volume, creating the conditions for the universe's hot, dense beginning. Thus, gravity was not just a force that emerged, it was integral to the very initial state of the universe and its subsequent unfolding. While gravity shapes the universe on its grandest scales, the other three fundamental forces, the strong nuclear force, the weak nuclear force, and the electromagnetic force, are equally crucial, governing the interactions of particles and the formation of all matter from the atomic level upwards. These forces emerged from a unified state as the universe cooled, each playing a distinct and vital role in the early cosmos. The strong nuclear force is, as its name suggests, the strongest of the four fundamental forces. Its primary role is to bind quarks together to form composite particles called hadrons, the most common of which are protons and neutrons. It also holds these protons and neutrons together within the nucleus of an atom, overcoming the electrical repulsion between positively charged protons. The strong force is unique because its strength increases with distance when quarks are separated, making it impossible to observe a free quark in isolation. Conversely, its strength decreases at very short distances, a property known as asymptotic freedom. This force is mediated by particles called gluons. The strong force separated from the grand unified force, which included the electroweak force, at an extremely early stage of the universe, during the Gut epoch, between 10 to the negative 43 seconds and 10 to the negative 36 seconds after the Big Bang. At temperatures above approximately 10 to the power of 29 degrees Celsius, quarks and gluons existed in a free, unconfined state known as a quark-gluon plasma. As the universe expanded and cooled below this critical temperature, around 10 to the negative 6 seconds, 1/1,000,000th of a second, after the Big Bang, when the temperature was about 2 trillion degrees Celsius, the strong force became strong enough to confine quarks into protons and neutrons. This process, called hadronization, was a pivotal event. Without the strong force, stable protons and neutrons, the building blocks of atomic nuclei could not have formed, and consequently no atoms or elements would exist. The strong force also played a crucial role during Big Bang nucleosynthesis, holding protons and neutrons together to form the nuclei of light elements like helium and lithium. The weak nuclear force is responsible for certain types of radioactive decay and for fundamental particle transformations. It governs processes where one type of quark or lepton can change into another, such as a neutron decaying into a proton, an electron, and an antineutrino. This force is mediated by massive particles called W and Z bosons. Unlike the strong and electromagnetic forces, the weak force is extremely short-ranged, acting only over distances smaller than the size of an atomic nucleus. It is also significantly weaker than the strong and electromagnetic forces. The weak force was unified with the electromagnetic force as the electroweak force at very high energies. This unification existed until the universe cooled to about 10 trillion degrees Celsius, approximately 10 to the negative 12 seconds, 1/1,000,000th of a second, after the Big Bang. At this point, the electroweak force broke symmetry, separating into the distinct electromagnetic and weak nuclear forces. The separation of the weak force was critical for several reasons. It played a role in establishing the slight matter-antimatter asymmetry in the early universe, as some theories suggest its interactions contributed to the excess of matter. Furthermore, the weak force was responsible for the decoupling of neutrinos from the rest of the matter and radiation at about 1 second after the Big Bang. Once neutrinos stopped interacting frequently via the weak force, they began to travel freely through space, forming the cosmic neutrino background. The weak force continues to be vital for processes like nuclear fusion in stars, where it facilitates the conversion of protons into neutrons, a necessary step for building heavier elements. The electromagnetic force governs the interactions between electrically charged particles. It is responsible for all chemical reactions, the binding of electrons to atomic nuclei to form atoms, and the emission and absorption of light. It is an infinite range force, meaning its influence extends indefinitely, though its strength decreases with distance. It is mediated by the photon, a massless particle. The electromagnetic force is much weaker than the strong force, but significantly stronger than the weak force and gravity at the atomic scale. The electromagnetic force separated from the weak force at about 10 to the negative 12 seconds after the Big Bang, as part of the electroweak symmetry breaking. Once distinct, the electromagnetic force began to play a crucial role in shaping the universe. For the first 380,000 years after the Big Bang, the universe was a hot, opaque plasma. Electrons were free and not bound to atomic nuclei. Photons were constantly scattering off these free charged electrons, preventing light from travelling freely. This made the universe opaque, like a dense fog. However, as the universe continued to expand and cool, its temperature eventually dropped to about 3,000 degrees Celsius, approximately 380,000 years after the Big Bang, At this critical temperature, the electromagnetic force became strong enough to bind the free electrons to the nuclei of hydrogen and helium, forming the first stable, neutral atoms. This event is known as recombination, or decoupling. Once electrons were bound into atoms, the photons were no longer scattered and could travel freely through space. This made the universe transparent to light for the first time. These photons, now travelling unimpeded, are what we detect today as the cosmic microwave background radiation, providing a direct snapshot of the universe at the moment it became transparent. The electromagnetic force continues to be fundamental to all aspects of our existence, from the light we see to the chemical bonds that form molecules and ultimately life. Following the dramatic events of the Big Bang and the formation of the first neutral atoms, the universe entered a prolonged period known as the Cosmic Dark Ages. This epoch, lasting for several 100 million years, was characterized by a profound absence of light sources as we understand them today. It was a time of cosmic quiet, where the universe, while transparent, remained largely unseen, waiting for the conditions to mature for the birth of the first stars and galaxies. The Dark Ages began approximately 380,000 years after the Big Bang, immediately after the process of recombination was largely complete. Before this point, the universe was a hot, dense and opaque plasma, where light was constantly scattering off free electrons. But once the temperature dropped sufficiently for electrons to combine with atomic nuclei to form neutral atoms, primarily hydrogen and helium, the universe became transparent. The light that was released during this event, the cosmic microwave background radiation, continued to stream freely through space. However, this was ancient light, and no new sources of energetic light had yet formed. During the Dark Ages, the universe was filled primarily with a diffuse neutral gas, about 75% hydrogen and 25% helium by mass, along with a significant amount of dark matter. Dark matter, an invisible and mysterious substance, does not interact with light or ordinary matter through the electromagnetic force, but it does exert gravitational pull. The cosmic microwave background photons, which were the first light released at recombination, continued to travel through this neutral medium, gradually cooling as the universe expanded. The temperature of the universe during the Dark Ages steadily decreased. At the beginning of this epoch, the temperature was about 3000 Kelvin, about 2,700 degrees Celsius. By the end of the Dark Ages, several 100 million years later, the temperature had cooled to perhaps 20 or 30 Kelvin, around negative 250 degrees Celsius, a temperature close to absolute zero. This continuous cooling was a direct consequence of the universe's ongoing expansion, which diluted the energy density of both matter and radiation. A defining characteristic of the Dark Ages was the absence of stars and galaxies. The universe was simply not yet ready to form these luminous structures. The neutral gas, though present, was too diffuse and too uniform to easily collapse under its own gravity to form dense clumps that could ignite nuclear fusion. The faint density fluctuations left over from the inflationary period and recorded in the cosmic microwave background were still very small, only variations of parts per 10,000. While these fluctuations were the seeds for future structure formation, gravity needed a very long time to amplify them sufficiently in a relatively cold, diffuse gas. Throughout this period, gravity, especially the gravitational pull of dark matter, was the dominant force at play in terms of structure formation. Dark matter, which makes up about 85% of the total matter in the universe, began to slowly pull itself together into gravitationally bound clumps known as dark matter halos. Because dark matter does not interact electromagnetically, it could collapse and form structures much more easily than ordinary matter, which was still relatively uniform and experiencing pressure from the residual radiation. These dark matter halos acted as gravitational wells, slowly attracting the neutral hydrogen and helium gas towards them. The process of structure formation during the Dark Ages was incredibly slow compared to later epochs. The gas was not dense enough to cool efficiently by radiating away energy, which is a necessary step for gas to collapse and form stars. Therefore, matter accumulated very gradually within the dark matter halos. The universe was a silent, dark canvas, with only the slowly strengthening gravitational tugs shaping its future. There were no bright sources of ultraviolet or visible light to illuminate the cosmos. The most significant light present was the ever-reddening cosmic microwave background, whose photons had been released hundreds of thousands of years earlier. Observing the cosmic dark ages directly presents an immense challenge for astronomers. Since there were no stars or galaxies emitting light in the visible or ultraviolet spectrum, our conventional telescopes cannot see into this period. It is a true observational gap in our cosmic history. However, physicists have theoretical methods to probe this era. One promising avenue is to look for the faint radio emission from neutral hydrogen atoms. Neutral hydrogen atoms can undergo a quantum transition, where the spin of their electron flips relative to the spin of their proton, emitting a photon with a wavelength of 21 centimeters. This 21 centimeter line is theorized to be the only detectable signal from the vast clouds of neutral hydrogen that filled the universe during the Dark Ages. Future radio telescopes, like the Square Kilometre Array, are designed to detect these faint signals, which would be redshifted to much longer wavelengths by the time they reach Earth, offering a unique window into this mysterious period. The Dark Ages came to an end with the birth of the very first stars and galaxies, an event known as reionization. As gas accumulated in the densest dark matter halos, it eventually became dense and cool enough to collapse and ignite nuclear fusion, forming the first stars, population 3 stars. These stars were massive, short-lived, and incredibly luminous, emitting powerful ultraviolet radiation. This radiation began to ionize the neutral hydrogen and helium gas in the universe, gradually stripping electrons from atoms and creating bubbles of ionized plasma. This process, known as reionization, slowly transformed the transparent but neutral universe back into an ionized, though much less dense state, bringing the Dark Ages to a close and ushering in the era of a lightened structure we observe today. The formation of the first stable, neutral atoms was a pivotal moment in the universe's early history, marking a profound transition from a hot, opaque plasma to a transparent gas-filled cosmos. This process, known as recombination, occurred approximately 380,000 years after the Big Bang. Driven by the continuous cooling of the expanding universe, it fundamentally changed the way light interacted with matter, setting the stage for the cosmic Dark Ages and the eventual birth of stars and galaxies. Before recombination, the universe was an extremely hot and dense plasma. Its primary constituents were free electrons, along with atomic nuclei that had formed during Big Bang nucleosynthesis, mainly protons, which are hydrogen nuclei, and helium nuclei, 2 protons and 2 neutrons. In this environment, the temperature was so high, above 3000 degrees Celsius, or about 3000 Kelvin, that any electrons attempting to bind with atomic nuclei would immediately be knocked free by energetic photons. This constant interaction between free electrons and photons meant that light could not travel freely through space. It was continuously scattered, making the universe opaque, much like a dense fog. The process of recombination began when the universe had expanded sufficiently that its temperature dropped to a critical point, around 3000 Kelvin. At this temperature, the average energy of the photons had fallen below the binding energy of hydrogen and helium atoms. The binding energy is the amount of energy required to remove an electron from an atom. When the universe was hotter, photons carried enough energy to ionize, strip electrons from, any newly formed neutral atoms. But once the temperature dropped below this threshold, photons no longer possessed enough energy to keep electrons from being captured by atomic nuclei. The formation of neutral hydrogen atoms was the most prevalent event during recombination, as hydrogen constituted about 75% of the universe's mass at that time. A free electron, encountering a positively charged proton, would be captured by the proton's electromagnetic pull. The electron would settle into a stable orbit around the proton, forming a neutral hydrogen atom. As the electron transitioned to lower energy levels within the newly formed atom, it would release photons. Similarly, free electrons combined with helium nuclei to form neutral helium atoms. This process was not instantaneous, but occurred over a period of tens of thousands of years as the temperature continued to fall gradually allowing more and more electrons to be captured. It is important to note that the term recombination is somewhat of a misnomer. It implies that electrons and nuclei were previously combined and are now combining again. However, this was the very first time that stable, neutral atoms could form in the universe. Prior to this, the universe was too hot for any atoms to exist, only free nuclei and electrons. Despite this semantic inaccuracy, the term recombination has become standard in cosmology. The formation of these neutral atoms had immediate and profound consequences for the universe. The most significant effect was that the universe, which had been opaque for hundreds of thousands of years, suddenly became transparent to light. Before recombination, free electrons were abundant, and they acted like tiny obstacles, scattering photons in every direction. It was like trying to see through a dense cloud. But once electrons became bound within neutral atoms, they were no longer free to scatter photons efficiently. The photons could now travel unimpeded through the vast expanses of newly transparent space. The light released during the recombination process, as electrons settled into lower energy states around nuclei, and the photons that were previously trapped are what we observe today as the cosmic microwave background, CMB radiation. The CMB is literally the first light of the universe that could travel freely. By the time this light reaches us billions of years later, its wavelengths have been stretched significantly by the expansion of the universe, shifting from visible and infrared light into the microwave part of the electromagnetic spectrum. Its temperature has cooled from 3000 Kelvin at recombination to about 2.7 Kelvin, about negative 270 degrees Celsius today. The existence of this cosmic microwave background, with its precise temperature and almost uniform distribution across the sky, is one of the strongest pieces of evidence supporting the Big Bang model and our understanding of the universe's early history. The formation of neutral atoms was also crucial for the subsequent development of cosmic structures. Before recombination, the universe was a plasma. Charged particles in a plasma resist clumping together due to electromagnetic repulsion and pressure from the intense radiation field. This made it difficult for gravity to pull matter into dense structures. However, once neutral atoms formed, the gas became electrically neutral. This allowed gravity to begin its long and slow work of pulling together the slight density enhancements, the seeds of future galaxies, that were imprinted during cosmic inflation. Without neutral atoms, the formation of stars and galaxies, which rely on the gravitational collapse of gas clouds, would have been severely hindered or impossible. Thus, the process of recombination, leading to the formation of the first neutral atoms, was a watershed moment in cosmic evolution. It ushered in the cosmic dark ages, transformed the universe from an opaque plasma into a transparent gas, and released the cosmic microwave background, providing an invaluable fossil record of the early cosmos. More importantly, it created the necessary conditions for gravity to eventually sculpt the vast and complex structures we observe in the universe today. The universe's early history was largely characterized by an impenetrable fog, a state of cosmic opacity that prevented light from traveling freely. For hundreds of thousands of years after the Big Bang, the cosmos was a dense, hot plasma where photons, the particles of light, were constantly scattered by free electrons. This continuous interaction meant that the universe was effectively opaque, much like looking into the heart of a star. Any light produced would immediately be absorbed and re-emitted in a random direction. However, a pivotal event approximately 380,000 years after the Big Bang radically changed this, allowing light to break free and transforming the universe into a transparent medium. This transformative event is known as decoupling, which occurred concurrently with the formation of the first neutral atoms, a process called recombination. Before this period, the universe was filled with a plasma consisting of positively charged atomic nuclei, mostly protons and helium nuclei, and negatively charged free electrons. These free electrons were the key to the universe's opacity. Photons, being massless particles that mediate the electromagnetic force, strongly interact with charged particles like free electrons. Every time a photon encountered a free electron, it would be scattered, similar to how light bounces off water droplets in a cloud. This constant scattering meant that a photon could travel only a very short distance before being deflected, preventing any coherent beam of light from propagating through the cosmos. As the universe continued its relentless expansion, it also cooled. By 380,000 years after the Big Bang, the temperature had dropped to approximately 3,000 Kelvin, about 2,700 degrees Celsius. This temperature was a crucial threshold. At energies corresponding to 3,000 Kelvin, the average kinetic energy of the free electrons and nuclei had fallen below the binding energy required to form stable, neutral atoms. This allowed the electromagnetic force to finally pull electrons into stable orbits around the positively charged nuclei. Free protons captured electrons to form neutral hydrogen atoms, and helium nuclei captured electrons to form neutral helium atoms. The formation of these neutral atoms was the direct cause of light breaking free. Once the electrons became bound within atoms, they were no longer free to interact strongly with photons. The primary scatterers of light in the early universe had effectively disappeared. Imagine a dense fog lifting. The water droplets, free electrons, have now condensed into larger, less obstructive forms, neutral atoms, allowing light to pass through. Similarly, photons, which were previously trapped in a constant dance of scattering, could now travel vast distances without interruption. This moment is often referred to as the surface of last scattering, because it represents the last time that the photons interacted significantly with matter. The light that broke free at this moment is what we observe today as the cosmic microwave background, CMB, radiation. These photons, released from the hot plasma 380,000 years after the Big Bang, have been travelling across the expanding universe ever since. As space has expanded over the past 13.8 billion years, the wavelengths of these photons have been stretched, or redshifted, from visible and infrared light into the microwave part of the electromagnetic spectrum. This is why we detect the CMB as faint microwave radiation, with a very cold temperature of about 2.7 Kelvin, about negative 270 degrees Celsius. The cosmic microwave background is one of the most powerful pieces of evidence supporting the Big Bang model. Its existence, its remarkable uniformity across the sky, and its precise temperature are direct predictions of the theory. The CMB provides a direct snapshot of the universe when it was still very young, allowing cosmologists to study its conditions at that pivotal moment. While the CMB is incredibly uniform, it also contains tiny temperature variations, on the order of parts per 10,000. These subtle anisotropies are crucial. They represent the slight density fluctuations that existed in the early universe, which were stretched to cosmic scales during inflation. After light broke free, these tiny variations acted as the gravitational seeds for all the large-scale structures we observe today, including galaxies and galaxy clusters. The universe becoming transparent had profound consequences for its subsequent evolution. Before decoupling, the universe was an impenetrable shroud, preventing us from seeing any further back in time with conventional light-based telescopes. The CMB is the earliest light we can ever hope to detect directly. This event also marked the end of the cosmic dark ages, a period where the universe, though transparent, lacked luminous sources like stars and galaxies. The light freed at decoupling streamed through this dark period, eventually passing through the first stars and galaxies as they ignited and began to reionize the universe. Thus, the moment light broke free was not just a fundamental change in the universe's optical properties, it was the start of its observable history and a crucial step towards the formation of the complex structures that fill the cosmos today. The universe, as we observe it today, is a vast and intricate tapestry of stars, galaxies, and cosmic structures. Yet, if we could peer back in time to its earliest moments, we would not see a universe filled with such luminous objects. Instead, we would encounter a pervasive, uniform glow of radiation, a faint echo of the Big Bang itself. This ancient light is known as the cosmic microwave background, or CMB, and it stands as one of the most compelling pieces of evidence for the universe's hot, dense beginning and its subsequent evolution. It is, in essence, the afterglow of creation, a fossilized record of the universe when it was still very young. The origin of the cosmic microwave background lies in a pivotal event that occurred approximately 380,000 years after the Big Bang. Before this time, the universe was an incredibly hot and dense plasma. Its primary constituents were positively charged atomic nuclei, mostly protons and helium nuclei, and negatively charged free electrons. In this state, the temperature was so high, above 3000 Kelvin, about 2700 degrees Celsius, that any electrons attempting to bind with atomic nuclei would immediately be knocked free by energetic photons. This constant interaction between free electrons and photons meant that light could not travel freely through space. Photons were continuously scattered by the free electrons, making the universe effectively opaque, much like a dense fog or the interior of a star. Any light produced would quickly be absorbed and re-emitted in a random direction, preventing a clear view through the cosmos. As the universe continued its rapid expansion, it also cooled. By the time it reached an age of about 380,000 years, its temperature had dropped to approximately 3000 Kelvin. At this critical temperature, the average energy of the photons had fallen below the binding energy of hydrogen and helium atoms. This allowed the electromagnetic force to finally pull electrons into stable orbits around the positively charged nuclei. Free protons captured electrons to form neutral hydrogen atoms, and helium nuclei captured electrons to form neutral helium atoms. This process is known as recombination, though it's a bit of a misnomer, as it was the first time these particles combined to form neutral atoms. The formation of these neutral atoms had an immediate and profound consequence. The universe suddenly became transparent to light. Once electrons were bound within atoms, they were no longer free to scatter photons efficiently. The primary obstacles to light propagation had effectively disappeared. The photons, which had been trapped in a constant dance of scattering, were now free to travel vast distances without interruption. This moment is often referred to as the surface of last scattering, because it represents the last time that the photons interacted significantly with matter. It is from this surface that the light we now detect as the CMB began its journey across the cosmos. The light that broke free at this moment has been travelling through the expanding universe ever since. As space has expanded over the past 13.8 billion years, the wavelengths of these photons have been stretched, or redshifted, from what was originally visible and infrared light into the microwave part of the electromagnetic spectrum. This is why it is called microwave background radiation. Its temperature has cooled from 3000 Kelvin at recombination to a mere 2.725 Kelvin, about negative 270.425 degrees Celsius, today just a few degrees above absolute zero. The cosmic microwave background was accidentally discovered in 1964 by Arno Penzias and Robert Wilson, two engineers working at Bell Labs. They were testing a new horn antenna designed for satellite communication and kept detecting a persistent uniform static or noise that came from every direction in the sky. Initially, they tried to eliminate all possible sources, even cleaning pigeon droppings from the antenna, but the signal persisted. Unbeknownst to them, a group of physicists at Princeton University, led by Robert Dicke, had independently predicted the existence of such a background radiation as a remnant of the Big Bang, and were building an antenna to detect it. When Penzias and Wilson learned of the Princeton group's work, they realized they had stumbled upon one of the most important discoveries in cosmology. Their discovery provided compelling observational evidence for the Big Bang theory and earned them the Nobel Prize in Physics in 1978. Subsequent observations have refined our understanding of the CMB. Early ground-based and balloon-borne experiments confirmed its properties. However, it was space-based missions that provided the most precise measurements. The Cosmic Background Explorer, or COBE satellite, launched by NASA in 1989, was the first to confirm that the CMB has a perfect blackbody spectrum, exactly as predicted for thermal radiation from the early universe. COBE also detected tiny temperature fluctuations, or anisotropies, in the CMB across the sky. These fluctuations, though incredibly small, only about 1 part in 100,000, were crucial. They represented the slight density variations that existed in the early universe, which were stretched to cosmic scales during the period of cosmic inflation. These tiny variations acted as the gravitational seeds from which all the large-scale structures we observe today, such as galaxies and galaxy clusters, eventually grew. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided even more detailed maps of the CMB anisotropies. The map's data allowed cosmologists to precisely determine several fundamental cosmological parameters, including the age of the universe, 13.8 billion years, the composition of the universe, about 5% ordinary matter, 27% dark matter, and 68% dark energy, and the geometry of space, flat. The Planck satellite, launched by the European Space Agency in 2009, provided the most precise and highest resolution maps of the CMB to date, further refining these parameters and providing even stronger support for the standard cosmological model, which includes inflation. The CMB provides several lines of evidence for the universe's origin and evolution. Firstly, its very existence confirms the idea of a hot, dense, early universe. If the universe had not started in such a state, there would be no pervasive afterglow of heat. Secondly, its black body spectrum is a strong indicator that the universe was once in thermal equilibrium, a state where all parts were in close contact and had the same temperature. Thirdly, the CMB's uniform temperature across vast, seemingly disconnected regions of the sky provides strong support for the theory of cosmic inflation, which explains how these regions were once in causal contact. Fourthly, the tiny anisotropies in the CMB are direct evidence for the initial density fluctuations that seeded structure formation, and their statistical properties align remarkably well with the predictions of inflation. Finally, the CMB acts as a surface of last scattering, meaning it is the earliest light we can ever hope to detect directly. Any light from before the CMB would have been trapped in the opaque plasma. Thus, the CMB provides an invaluable fossil record, allowing scientists to look back in time and reconstruct the universe's history from its fiery beginning. The vast and complex structures that populate our universe today, every star, every planet, every galaxy, and indeed every atom within us, are ultimately built from a surprisingly simple set of fundamental ingredients. These initial building blocks were primarily the lightest elements, hydrogen and helium gas, along with trace amounts of lithium. Their formation and initial distribution in the early universe were crucial steps that set the stage for all subsequent cosmic evolution, transforming a featureless plasma into a structured cosmos. The formation of these primordial building blocks occurred during a critical period known as Big Bang nucleosynthesis, or BBN. This process took place within the first few minutes after the Big Bang, specifically from about 1 minute to 3 minutes, when the universe had cooled sufficiently, but was still incredibly hot and dense. Before BBN, the universe was a superhot soup of fundamental particles, including quarks, leptons, and their antimatter counterparts. As the universe expanded and cooled, quarks combined to form protons and neutrons at about 1/1,000,000th of a second after the Big Bang. At this point, the universe contained a roughly equal number of protons and neutrons, but as it continued to cool, neutrons, which are slightly heavier and unstable when free, began to decay into protons. By the time BBN began, there were approximately 7 protons for every 1 neutron. When the universe's temperature dropped to about 1 billion degrees Celsius, roughly 1 billion Kelvin, conditions became suitable for nuclear fusion. Protons, which are essentially hydrogen nuclei, and neutrons began to combine to form the nuclei of light elements. The process unfolded in several steps. First, a proton and a neutron could fuse to form a nucleus of deuterium, which is a heavy isotope of hydrogen. Once deuterium nuclei formed, they could then capture another proton or neutron to form helium-3, 2 protons and 1 neutron, or helium-4, 2 protons and 2 neutrons. Helium-4 is particularly stable and was the most abundant heavier nucleus produced. Trace amounts of lithium-7 were also formed through the fusion of helium-4 and tritium, a very rare isotope of hydrogen with 1 proton and 2 neutrons, or helium-3 and helium-4. This period of nuclear fusion was very brief. It lasted only a few minutes because the universe was rapidly expanding and cooling. As the temperature continued to drop, it quickly became too cold and too dilute for nuclear fusion reactions to continue efficiently. This meant that only the lightest elements could be formed. Heavier elements such as carbon, oxygen, iron, and all the elements essential for planets and life could not be created during BBN. They require the much higher temperatures and pressures found in the cores of stars, or the explosive conditions of supernovae, processes that would only occur much later in cosmic history. The result of Big Bang nucleosynthesis was a universe composed of a very specific and predictable ratio of light elements. By mass, the primordial composition of the universe was approximately 75% hydrogen, the simplest element, consisting of a single proton, 25% helium, primarily helium-4 with trace amounts of helium-3, tiny traces of lithium. Lithium-7 was the most abundant, with even smaller amounts of lithium-6. This precise cosmic abundance of light elements is one of the most powerful and successful predictions of the Big Bang model. Observations of the oldest, most pristine gas clouds in the universe, which have not been significantly altered by stellar processes which would create heavier elements, show precisely these proportions. This remarkable agreement between theoretical predictions and astronomical observations provides strong evidence that the universe indeed began from a hot, dense state, and underwent the processes described by BBN. After Big Bang nucleosynthesis, the universe continued to expand and cool for hundreds of thousands of years. For the first 380,000 years after the Big Bang, these primordial building blocks, the hydrogen and helium nuclei, along with free electrons, existed in a hot, opaque plasma. During this period, light was constantly scattered by the free electrons, preventing it from travelling freely. Then, at about 380,000 years after the Big Bang, the universe cooled to approximately 3000 Kelvin. At this temperature, electrons were finally able to combine with the hydrogen and helium nuclei to form stable, neutral atoms. This event, known as recombination, marked the point where the universe became transparent to light, releasing the cosmic microwave background radiation. After recombination, the universe was filled with vast clouds of neutral hydrogen and helium gas, along with a significant amount of dark matter. This neutral gas, distributed throughout the cosmos, served as the fundamental raw material for all future structures. While the gas was initially very smooth and uniform, it contained tiny density fluctuations that were imprinted during the period of cosmic inflation. These fluctuations, though minuscule, variations of only parts per 10,000, were the crucial seeds for structure formation. The hydrogen and helium gas, along with the invisible dark matter, would slowly begin to accumulate in these slightly denser regions due to the relentless pull of gravity. The primordial hydrogen and helium were pure, in the sense that they contained virtually no heavier elements. This purity had significant implications for how the first stars would form. Unlike later generations of stars which formed from gas clouds enriched with heavier elements, often called metals by astronomers, the first stars had to form from this pristine, metal-free gas. This difference in composition affected their formation process, their properties, and their lifespans. Following the cosmic dark ages, a period when the universe was filled with neutral hydrogen and helium gas, but lacked any luminous sources, a transformative era began, the ignition of the very first stars. This event marked the end of the cosmic darkness and ushered in the epoch of reionization, where the universe was gradually re-illuminated and its neutral gas reionized. The formation of these pioneering stars, often referred to as population 3 stars, was a crucial step in the universe's evolution, as they were responsible for producing the first heavy elements and setting the stage for the formation of galaxies. The Dark Ages lasted for several 100 million years, from about 380,000 years after the Big Bang until roughly 200 to 400 million years later. During this time, the universe was transparent but cold and dark, with no stars or galaxies to emit light. The primary constituents were neutral hydrogen and helium gas, along with invisible dark matter. While gravity was slowly pulling this matter together, the gas was too diffuse and too pure, lacking heavier elements, to easily collapse and form stars. The process of forming the first stars began with the gravitational accumulation of matter. The tiny density fluctuations imprinted during cosmic inflation and later amplified by the gravitational pull of dark matter started to grow. Dark matter, which makes up about 85% of the total matter in the universe, began to clump together into gravitationally bound structures called dark matter halos. These halos acted as gravitational wells, slowly attracting the neutral hydrogen and helium gas towards their centers. As the gas fell into these dark matter halos, it became denser and hotter. For a gas cloud to collapse further and form stars, it needs to be able to cool efficiently. In modern star formation, heavier elements, which astronomers call metals, meaning anything heavier than helium, play a crucial role in cooling gas. These elements can radiate away energy more effectively, allowing the gas to shed heat and collapse to higher densities. However, the primordial gas in the early universe was almost entirely hydrogen and helium, completely devoid of these heavier elements. This made the cooling process for the first stars much more challenging. The primary cooling mechanism available to this pristine gas was the formation and dissociation of molecular hydrogen, H2. As the gas became denser, some hydrogen atoms could combine to form hydrogen molecules. These molecules could then radiate away energy, allowing the gas cloud to cool and contract further. However, molecular hydrogen is fragile and can be easily destroyed by ultraviolet radiation. This meant that the conditions for cooling were very specific and sensitive. Once the gas in the densest parts of the dark matter halos cooled sufficiently and became dense enough, gravity could overcome the internal pressure of the gas, leading to a runaway collapse. This collapse would continue until the core of the gas cloud became incredibly hot and dense, reaching temperatures of millions of degrees Celsius. At this point, nuclear fusion reactions would ignite, marking the birth of the very first stars. These first stars, often called population 3 stars, are purely theoretical, as none have been directly observed. They are predicted to have been very different from the stars we see today. Because they formed from pristine hydrogen and helium, they lacked the heavier elements that influenced the structure and evolution of modern stars. Theoretical models suggest that population 3 stars were extremely massive, likely hundreds or even thousands of times the mass of our Sun. Without heavier elements to help cool the gas and fragment it into smaller clumps, the primordial gas clouds tended to collapse into much larger stars. Very hot and luminous. Due to their immense mass, they would have burned through their nuclear fuel at an incredibly rapid rate, shining with extraordinary brightness. Short-lived. Their rapid burning meant they had very short lifespans, perhaps only a few million years, compared to the billions of years for stars like our Sun. The ignition of these first stars had profound consequences for the universe. Firstly, they mark the end of the cosmic dark ages by providing the first significant sources of light since the cosmic microwave background. Their intense ultraviolet radiation began to ionize the vast clouds of neutral hydrogen gas that filled the universe. This process, known as reionization, gradually stripped electrons from hydrogen atoms, transforming the neutral universe back into an ionized state. This reionization process was not instantaneous, but occurred in patchy regions around the first stars and galaxies, slowly spreading throughout the cosmos over hundreds of millions of years. Secondly, and perhaps most importantly, these first stars were the universe's first element factories. Through nuclear fusion in their cores, they began to synthesize heavier elements from the primordial hydrogen and helium. Elements like carbon, oxygen, nitrogen, and iron, the building blocks of rocky planets and life, were created in these stellar furnaces. When these massive, short-lived stars reached the end of their lives, they exploded as incredibly powerful supernovae. These first supernovae scattered the newly forged heavy elements into the surrounding intergalactic medium, enriching the pristine gas. This enrichment was crucial because it provided the necessary ingredients for the next generations of stars to form, which could then be smaller, longer-lived, and capable of forming planetary systems. Finally, the first stars also played a role in the formation of the first galaxies. While they were born within dark matter halos, their gravitational influence and the feedback from their powerful radiation and supernovae helped to gather more gas and dark matter, leading to the gradual assembly of the first small galaxies. These early galaxies then merged and grew over billions of years to form the magnificent structures we see today. Observing population 3 stars directly is extremely challenging due to their immense distance, short lifespans, and the fact that their light would be heavily absorbed by the intervening neutral hydrogen before reionization was complete. However, Astronomers search for indirect evidence, such as the signatures of reionization in the spectra of distant quasars, or by studying the properties of the oldest, most distant galaxies, which are thought to contain the descendants of these first stars. The James Webb Space Telescope, with its powerful infrared capabilities, is specifically designed to probe this early epoch and potentially catch glimpses of these very first luminous objects, shedding light on how the universe transitioned from darkness to the brilliance we witness today. The universe, in its early stages following the cosmic dark ages, was primarily a vast expanse of neutral hydrogen and helium gas, permeated by the unseen influence of dark matter. While the first stars had begun to ignite within the densest pockets of this primordial gas, the grand structures we now call galaxies were yet to fully form. The process of galaxy formation describes how these initial gas clouds and nascent stars gradually clumped together under the relentless pull of gravity, evolving into the rudimentary galactic structures that would serve as the blueprints for the colossal systems we observe today. The dominant force driving galaxy formation was gravity, working in concert with dark matter. Modern cosmological models, particularly those based on cold dark matter, suggest that dark matter played a pivotal role as the initial scaffolding for galaxy formation. Dark matter, which does not interact with light or other electromagnetic forces, could begin to collapse and form gravitationally bound structures much earlier and more efficiently than ordinary matter. These invisible structures are known as dark matter halos. These halos formed from the slight overdensities that were imprinted in the early universe during cosmic inflation, which were then slowly amplified by gravity throughout the Dark Ages. As dark matter halos grew and deepened their gravitational wells, they began to attract the surrounding baryonic or ordinary matter, the neutral hydrogen and helium gas, into their centers. This gas flowing into the potential wells created by the dark matter began to accumulate and compress. However, for this gas to collapse further and ignite stars, it needed to shed its internal energy, primarily through cooling. In the very early universe, the primordial gas was composed almost entirely of hydrogen and helium, lacking the heavier elements, which astronomers refer to as metals, that are abundant in later generations of stars and gas clouds. These heavier elements act as efficient coolants, radiating away energy more effectively and allowing gas to collapse to higher densities. In the metal-poor early universe, the primary cooling mechanism available was the formation of molecular hydrogen, H2. As the gas density increased within the dark matter halos, some hydrogen atoms combined to form these molecules. Molecular hydrogen can radiate away energy at specific wavelengths, allowing the gas to cool sufficiently to overcome its internal pressure and collapse further. However, molecular hydrogen is fragile and can be easily dissociated by ultraviolet radiation. This means that the conditions for forming the first gas clumps capable of forming stars were very sensitive and required shielding from early radiation sources. As the cooling gas continued to fall into the centers of the dark matter halos, its density increased dramatically. Eventually, within the most massive and dense of these gas clumps, the conditions became suitable for the ignition of nuclear fusion, leading to the formation of the very first stars, the population 3 stars. These initial stars were often very massive, hot, and short-lived, burning through their nuclear fuel rapidly. The formation of these first stars within the nascent galactic structures provided critical feedback mechanisms that influenced the subsequent stages of galaxy formation. The intense ultraviolet radiation emitted by these massive stars began to ionize the surrounding neutral hydrogen gas, creating bubbles of ionized plasma. This process, known as reionization, slowly spread throughout the universe, gradually stripping electrons from atoms and transforming the transparent but neutral cosmos back into an ionized, though much less dense state. While this reionization made the universe transparent to light again, the heating of the intergalactic gas by this radiation could also prevent gas from collapsing into smaller structures, potentially suppressing star formation in some regions. Furthermore, when these massive first stars ended their lives, they exploded as incredibly powerful supernovae. These first supernovae were crucial because they dispersed the newly forged heavy elements, produced through nuclear fusion in their cores, into the surrounding intergalactic medium. This enrichment with metals was vital for the next generations of star formation. Gas clouds containing even trace amounts of heavier elements could cool much more efficiently, allowing them to fragment into smaller clumps and form a wider range of stars, including smaller, longer-lived stars like our Sun. The shock waves from these supernovae could also trigger new star formation by compressing gas, or, conversely, blow gas out of shallow potential wells, regulating the growth of early galaxies. The first galaxies were likely much smaller and less massive than the grand spiral and elliptical galaxies we observe in the local universe today. They were probably more akin to the dwarf galaxies that orbit larger galaxies. These early galactic structures would have been relatively irregular in shape, often clumpy, and dominated by active star formation. They typically contained a high fraction of gas, which was still relatively pristine. The processes of star formation within these early clumps were likely chaotic and violent, given the massive nature of the first stars and their explosive deaths. The formation of these rudimentary galaxies was not a singular event, but an ongoing process driven by hierarchical merging. Smaller dark matter halos and their embedded gas clumps would frequently merge with each other, gradually building up larger and larger structures. These early mergers were a key driver of growth, allowing small proto-galaxies to coalesce into more substantial systems. Evidence from deep field observations, particularly from telescopes like the Hubble Space Telescope, and more recently the James Webb Space Telescope, reveals a universe in its infancy filled with numerous small, irregularly shaped galaxies that are actively merging. These high redshift observations provide direct visual evidence of the early stages of galaxy formation and growth. Computer simulations have become indispensable tools for understanding galaxy formation, starting from the initial conditions observed in the cosmic microwave background, the tiny density fluctuations. These simulations, which incorporate the physics of dark matter, baryonic gas, gravity, and various feedback mechanisms, can successfully reproduce the cosmic web and the types of galaxies observed at different epochs. They show how dark matter halos grow through mergers, attracting gas, forming stars, and eventually leading to the complex galactic ecosystems we see today. The process of galaxy formation is thus a continuous saga of gravitational collapse, gas dynamics, star formation, and mergers unfolding over billions of years. Once the universe transitioned from the pristine conditions of the Dark Ages and the first rudimentary galaxies began to form, a new phase of cosmic evolution commenced, the continuous growth and transformation of these galactic structures. Galaxies are not static entities. They evolve dynamically over cosmic time, driven primarily by two fundamental processes: the accretion of fresh gas from their surroundings and, crucially, mergers with other galaxies. This hierarchical growth has led to the vast and diverse population of galaxies we observe today, from majestic spirals to colossal ellipticals. The primary mechanism for galaxy growth is the hierarchical merging of smaller structures into larger ones. This process is a fundamental prediction of the cold dark matter model, which posits that the universe's structure formed from the bottom up, with small dark matter halos and their embedded galaxies forming first, then merging to create progressively larger systems. In the early universe, galaxies were generally smaller, more numerous, and more irregular in shape. Gravitational interactions between these closely packed early galaxies were frequent, leading to countless mergers. Mergers can be broadly categorized into two types. First, minor mergers occur when a larger galaxy absorbs a much smaller companion, such as a dwarf galaxy. These events are relatively common and contribute to the gradual, steady growth of massive galaxies without necessarily causing dramatic changes to their overall morphology. The Milky Way, for instance, is currently absorbing several dwarf galaxies, a process that adds stars, gas, and dark matter to its growing halo. Evidence of past minor mergers can be seen in stellar streams, trails of stars that were tidally stripped from the smaller galaxy as it was torn apart by the larger one's gravity. Second, major mergers involve the collision of two galaxies of comparable size. These are far more energetic and disruptive events, capable of profoundly altering the structure and evolution of the merging galaxies. When two large galaxies collide, their immense gravitational pulls distort each other, pulling out long tidal tails of stars and gas. The individual stars rarely collide because the space between them is so vast, but the gas clouds collide fiercely. These gas collisions compress the gas, triggering intense bursts of star formation, often referred to as starbursts, which can produce stars at rates hundreds of times higher than in normal galaxies. Major mergers also play a crucial role in transforming galaxy morphology. Spiral galaxies, which are characterized by flat disks and prominent spiral arms, are thought to be particularly susceptible to morphological changes during major mergers. The violent gravitational disturbances and gas compression during a major merger can disrupt the delicate disk structure, causing stars and gas to settle into a more rounded elliptical shape. It is widely believed that many of the large elliptical galaxies we observe today are the end products of one or more major mergers between spiral galaxies in the distant past. This suggests an evolutionary path where early, gas-rich spirals can transform into elliptical galaxies through violent mergers. In addition to mergers, galaxies also grow through the accretion of fresh gas from the surrounding intergalactic medium. Galaxies sit within immense reservoirs of gas that extend far beyond their visible stellar disks. Over cosmic time, this gas, enriched by heavy elements expelled from supernovae of previous generations of stars, slowly cools and flows into the gravitational potential wells of galaxies. This inflowing gas provides a continuous fuel supply for ongoing star formation, allowing galaxies to steadily increase their stellar mass. Without this continuous gas accretion, galaxies would eventually run out of raw material for new stars and cease their growth. The environment in which galaxies reside also significantly influences their growth and evolution. Galaxies within dense environments, such as galaxy clusters, experience more frequent interactions and mergers. Within these clusters, galaxies can also be stripped of their gas by the hot diffuse gas that permeates the cluster, a process known as ram pressure stripping. This stripping can abruptly halt star formation in affected galaxies, turning them red and dead, meaning they contain older, redder stars and no longer actively form new ones. Conversely, galaxies in less dense field environments might grow more slowly but steadily through gas accretion, maintaining their spiral morphology for longer. The distribution of galaxies in the universe is not random. They are organized into a vast interconnected network known as the cosmic web, consisting of filaments, sheets, and enormous empty regions called voids. Galaxies tend to form and grow along these filaments and at the nodes where filaments intersect. Mergers are more likely to occur along these filaments as galaxies fall towards each other, following the gravitational pathways of the cosmic web. This large-scale structure provides the framework within which galaxy growth and evolution unfold. Observational evidence for growing galaxies through mergers and accretion is abundant. We can directly observe galaxies in the process of colliding and merging, like the famous antennae galaxies, which clearly show distorted structures, tidal tails, and bursts of star formation. Distant high redshift galaxies, observed by powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope, often appear irregular, clumpy, and show signs of active merging, consistent with a universe where hierarchical growth was rampant in the past. Stellar streams in the Milky Way's halo provide fossil records of past minor mergers. Computer simulations have become indispensable tools for modeling the complex process of galaxy growth. These simulations, starting from the initial density fluctuations in the early universe and incorporating the dynamics of dark matter, baryonic gas, star formation, and feedback processes from stars and black holes, successfully reproduce the observed distribution and properties of galaxies across cosmic time. They vividly demonstrate how small clumps merge to form larger galaxies, how gas is accreted, and how different galaxy types emerge through these dynamic processes. The story of growing galaxies is thus one of continuous transformation, driven by gravity, gas flow, and repeated cosmic collisions that have built the grand structures we see across the universe today. Black holes, particularly the supermassive variety, are among the most enigmatic and powerful objects in the cosmos. Far from being mere cosmic vacuum cleaners, these gravitational behemoths, weighing millions to billions of times the mass of our Sun, play a crucial and dynamic role in shaping the evolution of the galaxies they inhabit. Their influence extends far beyond their immediate vicinity, impacting star formation, galaxy morphology, and the overall growth of cosmic structures. Supermassive black holes, SMBHs, are found at the centers of nearly all massive galaxies, including our own Milky Way, which hosts Sagittarius A star, a black hole weighing about 4 million solar masses. The precise mechanisms of their formation remain an active area of research, but several theories exist. One idea suggests that they grew from seed black holes left over from the collapse of the very first massive stars, population 3 stars, in the early universe. These smaller black holes would then have grown over cosmic time by accreting vast amounts of gas and dust from their surroundings, and by merging with other black holes during galaxy collisions. Another theory proposes that some supermassive black holes might have formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. A third possibility involves the runaway collapse of dense star clusters, where repeated stellar collisions could lead to the formation of an intermediate mass black hole that then grows into a supermassive one. One of the most striking pieces of evidence for the intimate connection between supermassive black holes and their host galaxies is the empirical M-sigma relation. This observed correlation shows a tight relationship between the mass of a supermassive black hole and the velocity dispersion, a measure of the random motions of stars in the bulge of its host galaxy. This relationship suggests that the growth of the central black hole and the growth of the galaxy's central bulge are intrinsically linked, implying a process of coevolution. The black hole does not simply sit passively at the center, it actively participates in the galaxy's development. The primary way supermassive black holes influence galaxy evolution is through what is known as active galactic nucleus, AGN, feedback. When a supermassive black hole actively accretes matter, drawing in surrounding gas, dust, and even stars, it becomes an active galactic nucleus, or AGN. This accretion process is incredibly efficient, releasing enormous amounts of energy across the electromagnetic spectrum, making AGN, such as quasars and blazars, some of the most luminous objects in the universe. Only a small fraction of the accreting matter is needed to power these brilliant emissions. The energy released by an AGN can dramatically affect the surrounding galaxy in several ways. The intense radiation, powerful winds, and energetic jets launched from the vicinity of the black hole can interact with the gas in the galaxy. This interaction can heat the gas, preventing it from cooling down and forming new stars. It can also expel vast quantities of gas out of the galaxy entirely, a process known as outflows. These outflows can sweep away the raw material for star formation, effectively quenching star formation in the host galaxy. This negative feedback mechanism is thought to be crucial for explaining why star formation eventually ceases in massive elliptical galaxies, turning them into red and dead systems that contain only older, redder stars and no longer actively produce new ones. Without AGN feedback, massive galaxies might have formed many more stars than observed, becoming far larger and brighter. Conversely, AGN feedback can also act as positive feedback in some scenarios. The powerful winds or jets from an AGN might locally compress gas in other regions of the galaxy, triggering new bursts of star formation. However, the prevailing view emphasizes the negative feedback role of AGN, particularly in massive galaxies. The role of supermassive black holes is particularly prominent during the quasar epoch, which occurred in the early universe, roughly 1 billion to 3 billion years after the Big Bang. During this period, supermassive black holes were at their most active, accreting matter at prodigious rates and shining as incredibly luminous quasars. This intense activity coincided with a period of rapid galaxy growth and star formation. It is believed that the feedback from these powerful quasars was essential for regulating the growth of the most massive galaxies, ensuring they did not become too large and prevented them from forming stars too quickly. Supermassive black holes primarily grow by accreting gas and dust from their immediate surroundings. When gas falls towards the black hole, it forms an accretion disk that heats up to millions of degrees Celsius due to friction, emitting X-rays and ultraviolet light. If the black hole grows sufficiently massive, it can also grow by merging with other black holes during galaxy collisions. When two galaxies merge, their central supermassive black holes can spiral inward and eventually coalesce, forming an even more massive black hole. gravitational wave observatories are beginning to detect the ripples in space-time caused by the mergers of smaller black holes, and future observatories aim to detect similar events from supermassive black hole mergers. Observational evidence for the role of supermassive black holes comes from various sources. Their gravitational influence on stars orbiting the galactic center, as seen in our Milky Way, allows us to measure their masses. X-ray and radio telescopes detect the powerful emission from active galactic nuclei and their associated jets. The detection of massive outflows of gas from active galaxies provides direct evidence of feedback. The tight correlation between black hole mass and galaxy bulge properties, M-sigma relation, further underscores their intertwined evolution. Stars, the luminous beacons of the cosmos, are not eternal. Like all things in the universe, they undergo a life cycle, from their birth in vast clouds of gas and dust to their eventual demise, which can range from a gentle fading to a spectacular explosion. The path a star takes through its evolution is primarily determined by its initial mass, but all stars follow a fundamental sequence of stages driven by the interplay of gravity and nuclear fusion. Understanding stellar evolution is crucial to comprehending how the universe has transformed over billions of years, creating the elements necessary for planets and life. The journey of a star begins in a nebula, a giant cloud of interstellar gas and dust. These clouds, often vast and cold, are mostly composed of hydrogen and helium, along with trace amounts of heavier elements dispersed by previous generations of stars. Within these nebulae, gravity is the sculptor. While the cloud as a whole might be stable, turbulence or external triggers, such as the shock wave from a nearby supernova, a galactic density wave, or a collision with another cloud, can cause denser pockets within the nebula to become gravitationally unstable. As these pockets of gas and dust become sufficiently dense, they begin to collapse under their own gravity. As a region of the cloud collapses, it spins faster due to the conservation of angular momentum, and the material begins to flatten into a rotating disk, known as a protoplanetary disk or proplide. At the center of this disk, matter continues to fall inward, forming a dense, hot core called a protostar. The temperature and pressure within the protostar rise dramatically due to gravitational compression. During this phase, protostars often emit powerful bipolar jets of gas from their poles, which help to shed excess angular momentum and clear away surrounding material. This pre-main sequence phase can last for hundreds of thousands to tens of millions of years, depending on the star's eventual mass. A star truly begins its life as a main sequence star when its core temperature and pressure become high enough, around 10 million degrees Celsius, to ignite sustained nuclear fusion. For stars like our Sun, this involves the proton-proton chain reaction, where 4 hydrogen nuclei, protons, fuse to form one helium nucleus, releasing a tremendous amount of energy in the process. For more massive stars, a different process called the CNO cycle, carbon-nitrogen-oxygen cycle, is more dominant, also fusing hydrogen into helium but using carbon, nitrogen and oxygen as catalysts. This nuclear fusion generates an outward pressure that precisely balances the inward pull of gravity, creating a stable equilibrium. The star spends the vast majority of its life, about 90% in this main sequence phase, steadily converting hydrogen into helium in its core. The colour and luminosity of a main sequence star are directly related to its mass. More massive stars are hotter, bluer and brighter, while less massive stars are cooler, redder and dimmer. The lifespan on the main sequence is inversely related to mass. Massive stars burn through their fuel much more quickly, living for only a few million years, whereas smaller stars can live for hundreds of billions of years. Our Sun, an intermediate mass star, has been on the main sequence for about 4.6 billion years and is expected to remain there for another 5 billion years. The next stages of stellar evolution diverge significantly based on the star's initial mass. For low-mass stars like our Sun, stars with initial masses less than about 8 times the mass of our Sun, the journey after the main sequence is relatively gentle. When a low-mass star exhausts the hydrogen fuel in its core, fusion stops, and the core begins to contract under gravity. This contraction heats the core, which in turn heats the hydrogen in a shell surrounding the core, igniting hydrogen shell burning. The increased energy output from this shell pushes the star's outer layers outward, causing them to expand dramatically and cool, transforming the star into a red giant. The Sun will expand to engulf Mercury, Venus, and possibly Earth when it becomes a red giant. Inside the red giant, the helium-rich core continues to contract and heat. For stars similar to the Sun, when the core reaches about 100 million degrees Celsius, helium fusion ignites explosively in a helium flash. For slightly more massive stars, helium fusion begins more smoothly. Helium fuses into carbon and oxygen through the triple alpha process. After the helium in the core is exhausted, the star enters the asymptotic giant branch, AGB phase, where it has both hydrogen and helium-burning shells around a degenerate carbon-oxygen core. During this phase, the star becomes very unstable, undergoing thermal pulses and expelling much of its outer envelope through strong stellar winds. Eventually, the outer layers of the AGB star drift away into space, forming a beautiful, often intricately shaped cloud of gas called a planetary nebula. These nebulae are relatively short-lived, lasting only tens of thousands of years. What remains at the centre is the super-dense hot core of the star now exposed. This remnant is a white dwarf, typically about the size of Earth, but containing roughly the mass of the Sun. A white dwarf no longer undergoes nuclear fusion. It slowly cools over billions of years, radiating away its residual heat, eventually becoming a cold, dark, black dwarf. A theoretical object, as the universe is not old enough for any to have formed. For high-mass stars, those with initial masses greater than about 8 times the mass of our Sun, the evolutionary path is far more dramatic. These stars are hotter, brighter, and burn through their hydrogen fuel much more quickly, spending only a few million years on the main sequence. After exhausting hydrogen in their cores, they too expand into red supergiants. However, their immense mass allows them to achieve the higher temperatures and pressures necessary to fuse increasingly heavier elements in their cores. They undergo successive stages of core burning. Helium fuses to carbon, then carbon fuses to neon and magnesium, neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally silicon fuses into iron and nickel. Each successive fusion stage requires higher temperatures and pressures and lasts for a shorter period, with silicon burning lasting only a few days. During these advanced stages, the star develops an onion-like layered structure, with shells of different elements undergoing fusion around an inert core. The formation of an iron core is the critical turning point for a massive star. Iron fusion does not release energy. Instead, it consumes energy. Once the core is composed primarily of iron, fusion stops, and the core loses its ability to support itself against the crushing force of gravity. In a catastrophic event, the iron core collapses rapidly in a fraction of a second. This collapse creates an extreme density, forming a neutron star, a super-dense object composed almost entirely of neutrons, or, if the core is massive enough, a black hole. The sudden stop of the collapse causes the outer layers of the star to rebound off the incredibly dense core, triggering a massive outward explosion known as a Type II supernova. A supernova explosion is an incredibly luminous event, briefly outshining an entire galaxy. It disperses vast quantities of newly synthesized heavy elements, including those heavier than iron, into the interstellar medium. The remnant left behind depends on the initial mass of the star. For stars with initial masses between about 8 and 30 times the mass of the Sun, the core collapses to form a neutron star, an object only about 20 kilometers in diameter, but with a mass greater than the Sun, so dense that a teaspoon of its material would weigh billions of tons. For the most massive stars, those over about 30 solar masses, the core collapses completely, overcoming even neutron degeneracy pressure, and forms a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Thus, the life cycles of stars, from their birth in cosmic nurseries to their varied and dramatic deaths, are fundamental to the evolution of the universe. They are the engines of nuclear fusion, creating the elements that build planets, and eventually life. The remnants of dead stars, white dwarfs, neutron stars, and black holes, along with the dispersed elements from supernovae, continue to shape the cosmos, influencing subsequent generations of stars and galaxies. The universe began with remarkably simple elemental composition. According to the Big Bang nucleosynthesis theory, the very early universe, within its first few minutes, produced almost exclusively the lightest elements: hydrogen, about 75% by mass, helium, about 25%, and trace amounts of lithium. All the heavier elements, from carbon and oxygen, which are vital for life, to iron, silicon, gold, and uranium, were not present in the primordial cosmos. These heavier elements, which collectively make up only about 2% of the ordinary matter in the universe, were painstakingly forged inside stars and dispersed into space through cataclysmic stellar deaths. The process of making elements is thus a continuous cosmic cycle, intimately tied to stellar evolution. The primary mechanism for creating elements heavier than lithium is nuclear fusion within stars, a process often referred to as stellar nucleosynthesis. Stars are essentially giant cosmic furnaces, where extreme temperatures and pressures in their cores force atomic nuclei to combine, releasing immense amounts of energy in the process. The first stage of element production in any star occurs during its long main sequence phase, where it fuses hydrogen into helium in its core. For stars like our Sun, this occurs through the proton-proton chain reaction, where 4 hydrogen nuclei, protons, combine in a series of steps to form one helium nucleus. For more massive stars, a different process called the CNO cycle, carbon-nitrogen-oxygen cycle, dominates, using existing carbon, nitrogen, and oxygen as catalysts to convert hydrogen into helium. These processes are responsible for producing the vast majority of helium in the universe, beyond what was created in the Big Bang. Once a star exhausts the hydrogen fuel in its core, its evolution diverges based on its mass, leading to different pathways for element creation. In low-mass stars, like the Sun, after the hydrogen in the core is depleted, the core contracts and heats, igniting a shell of hydrogen burning around it. This leads to the star expanding into a red giant. When the core of the red giant becomes hot and dense enough, around 100 million degrees Celsius, helium fusion begins through the triple alpha process. In this reaction, 3 helium nuclei, alpha particles, fuse together to form one carbon nucleus. Subsequently, some carbon nuclei can fuse with another helium nucleus to form oxygen. Therefore, red giant stars are the primary cosmic factories for carbon and oxygen. Later, during the asymptotic giant branch, AGB, phase, low-mass stars can also slowly create some heavier elements up to bismuth, or led through a process called the S process, slow neutron capture. In the S process, atomic nuclei capture free neutrons one at a time. If the resulting nucleus is unstable, it undergoes beta decay, transforming a neutron into a proton, thereby increasing its atomic number and creating a new, heavier element. This process occurs relatively slowly, allowing time for beta decay to happen before more neutrons are captured. In high-mass stars, those with initial masses greater than about 8 times the mass of our Sun, the element-making process is far more extensive and rapid. After exhausting hydrogen, these stars undergo successive stages of nuclear fusion in their cores, burning progressively heavier elements. This creates an onion-like layered structure, with lighter elements fusing in outer shells and heavier elements fusing closer to the core. Carbon burning, carbon nuclei fuse to form elements like neon, magnesium, and sodium. Neon burning, neon nuclei fuse to produce oxygen and magnesium. Oxygen burning, oxygen nuclei fuse to form silicon, sulfur, and argon. Silicon burning, silicon nuclei fuse to produce heavier elements, culminating in the formation of iron and nickel. This is the final stage of energy-releasing fusion in the core of a massive star. The formation of an iron core is a critical turning point. Unlike fusion reactions involving lighter elements, the fusion of iron nuclei does not release energy. Instead, it consumes energy. This means that once the core is composed primarily of iron, it can no longer generate the outward pressure needed to support the star against the immense inward pull of gravity. This lack of energy generation leads to the rapid and catastrophic collapse of the stellar core. This core collapse triggers a Type II supernova, an incredibly powerful explosion that briefly outshines an entire galaxy. Supernovae are crucial for making elements in two primary ways. First, the extreme conditions during the core collapse and the subsequent shockwave lead to explosive nucleosynthesis. The intense flood of neutrons created during the collapse and explosion allows for the R process, rapid neutron capture. In the R process, atomic nuclei rapidly capture a large number of neutrons before they have a chance to undergo beta decay. This quickly builds up very heavy, neutron-rich, unstable nuclei, which then undergo a series of beta decays to form stable, neutron-rich isotopes of elements heavier than iron, including many of the heaviest elements in the periodic table, such as gold, platinum, silver, uranium, and plutonium. The R process is the dominant source for about half of the elements heavier than iron. Second, the supernova explosion violently disperses all the newly synthesized elements from both the star's previous fusion stages and the supernova itself into the surrounding interstellar medium. Without these cosmic explosions, the elements forged in stellar cores would remain locked within stellar remnants. Beyond these primary stellar processes, other events also contribute to element formation. Type Ia supernovae result from the thermonuclear runaway of white dwarfs in binary star systems. These explosions do not involve core collapse but are crucial sources of vast amounts of iron, nickel, silicon, and other intermediate mass elements, as well as some heavier elements. More recently, the mergers of neutron stars have been identified as a significant, if not primary, source of the heaviest R process elements, including gold, platinum, and rare earth elements. The detection of gravitational waves from a neutron star merger in 2017, followed by the observation of its electromagnetic afterglow, a kilonova, provided direct evidence for the creation of heavy elements in such events. Finally, cosmic rays, high-energy particles travelling through space, can cause spallation when they collide with heavier nuclei, breaking them apart to form lighter elements like lithium, beryllium, and boron, which were not significantly produced during Big Bang nucleosynthesis. The continuous cycle of star formation, stellar death, especially supernovae and neutron star mergers, and the dispersal of newly formed elements into the interstellar medium is known as galactic chemical evolution. Over billions of years, each successive generation of stars forms from gas clouds that are progressively more enriched with heavier elements. This enrichment is fundamental because the presence of elements heavier than helium is essential for the formation of rocky planets, which require elements like silicon, oxygen, iron, and carbon. It is this cosmic alchemy that has provided the raw materials for the formation of complex structures, including our own planet Earth and the very building blocks of life itself. The formation of our Sun, approximately 4.6 billion years ago, represents a crucial chapter in the universe's ongoing story of creation. Unlike the very first stars, which formed from pristine hydrogen and helium, our Sun is a second generation, or later, star, meaning it was born from a cloud of gas and dust that had already been enriched with heavier elements by previous generations of massive, short-lived stars. This enrichment was not only essential for the Sun's own properties, but also for the subsequent formation of the rocky planets, including Earth, that now orbit it. The process of the Sun's formation is a detailed example of how stars, particularly those of intermediate mass, come into being within the vastness of the cosmos. The journey of our Sun began within a giant molecular cloud, GMC, a vast, cold and dense aggregation of interstellar gas and dust. These clouds are the nurseries of stars, stretching for tens to hundreds of light years across, and containing enough material to form thousands of stars like our Sun. The particular GMC that gave birth to our solar system was not pristine primordial gas. It had been enriched by the remnants of supernovae from earlier, massive stars. This enrichment is evidenced by the presence of elements heavier than helium in the Sun, and planets, such as carbon, oxygen, iron, silicon, and many others, which could only have been forged in the cores and explosive deaths of previous stars. While a giant molecular cloud is generally stable, its internal balance can be disrupted by an external trigger, causing a portion of it to become gravitationally unstable and begin to collapse. The most widely accepted theory for the trigger that initiated the collapse of the cloud that formed our Sun is a shock wave from a nearby supernova explosion. the expanding shockwave from a dying massive star would have compressed a region of the GMC, increasing its density sufficiently for gravity to take over. Other possible triggers include collisions with other molecular clouds or density waves propagating through the spiral arms of our galaxy. Once a dense core within the cloud begins to collapse under its own gravity, it starts to spin faster due to the conservation of angular momentum, much like a spinning ice skater pulls in their arms to increase their rotation rate. As the collapsing material spins, it also flattens into a rotating disk, known as a protoplanetary disk or proplid. This disk, composed of gas and dust, would eventually be the birthplace of the planets in our solar system. The vast majority of the collapsing material, however, falls towards the center of the disk, where the protostar is forming. At the very center of the disk, the accumulating mass forms a protostar. As more and more material falls onto the protostar, gravitational compression causes its core to heat up dramatically. During this phase, protostars are often characterized by powerful bipolar jets and outflows of gas emitted from their poles. These jets play a crucial role in shedding excess angular momentum from the collapsing system, preventing the protostar from spinning too rapidly and allowing more material to fall onto the central star. These jets also clear away some of the surrounding gas and dust, eventually making the nascent star visible. For a period of about 1 million to 10 million years, the Sun would have existed as a T-Tauri star, a type of pre-main sequence star. During this phase, the Sun was still accreting mass from its surrounding disk, highly active with strong stellar winds and flares, and was not yet powered by stable nuclear fusion in its core. The protostar continued to contract and heat up under gravity. The critical moment in the Sun's formation came when its core temperature and pressure reached the immense levels required to ignite sustained nuclear fusion. For a star of the Sun's mass, this occurs when the core temperature reaches approximately 10 million degrees Celsius. At this temperature, hydrogen nuclei, protons, have enough kinetic energy to overcome their mutual electrostatic repulsion and fuse together to form helium nuclei through the proton-proton chain reaction. This process releases a tremendous amount of energy, creating an outward pressure that finally balances the inward pull of gravity. Once nuclear fusion begins in a stable and self-sustaining manner, the Sun enters the main sequence phase of its life. This marks its true birth as a star. The Sun has been on the main sequence for about 4.6 billion years and is expected to remain there for another 5 billion years, steadily converting hydrogen into helium in its core. During this long, stable period, the Sun provides the steady light and heat that are essential for life on Earth. The formation of the Sun from an enriched cloud of gas and dust had another profound consequence: the formation of its planetary system. The leftover material in the protoplanetary disk, which did not fall into the central protostar, began to clump together through processes of accretion. Dust grains stuck together to form pebbles, then rocks, then planetesimals, and eventually the planets, moons, asteroids, and comets that make up our solar system. The presence of heavier elements in this disk was absolutely crucial for the formation of rocky planets like Earth. Without these metals, elements heavier than helium, only gas giants could have formed, or perhaps no planets at all. Thus, our Sun's formation from a chemically enriched environment directly enabled the birth of a planetary system capable of hosting life,